Welcome to the CNN Architecture Mind Atlas, a conceptual and architectural journey that maps the evolution of convolutional neural networks and modern vision models. This course is not a simple walkthrough. It's a deep dive into the why behind model structures, blending historical context with the guiding design philosophies that shaped these breakthroughs. You'll trace the detailed narrative of CNNs from the foundational LeNet to the groundbreaking vision transformers. We'll explore core ideas like skip connections, bottleneck design, and parameter efficiency, using visual analogies and hands-on concepts to enhance your understanding. This tutorial is designed for anyone, from beginners to advanced professionals, who wants to build a strong foundation in deep learning architectures and understand the mindset behind modern network design. Muhammad Al-Abra developed this course.
Hey everyone, welcome to this full 5-hour deep dive into the world of convolutional neural networks. In this course, we're going to break down the evolutions of CNNs from the early days of LeNet and AlexNet all the way to cutting-edge models like ResNet, Inception, and even vision transformers. But this isn't just a history lesson. We'll uncover why these models were built the way they are, what problems they solved, and how they changed the game in computer vision. Whether you're new to deep learning or sharpening your skills, this tutorial will guide you step by step with explanations, visuals, and real-world insights. So grab your coffee and let's dive in. What if I told you that every neural network architecture, LeNet to vision transformers, is more than a set of layers? That beneath every convolution and every connection lies a philosophy, a world view about how machines should perceive, learn, and generalize. Welcome to CNN Architect Mind, a philosophical atlas tracing the monumental evolution of convolutional neural networks and their successes. In this journey, we won't just analyze models, will excavate their core ideas, their motivations, and the architectural revolutions they ignited. This is not merely a history of code, this is the intellectual heritage of deep learning. What this atlas covers together will traverse a timeline of milestones, each a leap in how machines understand the world. From LeNet 5, which taught machines to see like children, learning to read from raw pixels, to AlexNet, the architecture that restored deep learning using GPUs, graphical processing units, and ReLUs, rectified linear units, to break open the modern AI renaissance. Then came VGG, whispering the lesson: depth with simplicity can rival handcrafted ingenuity. With GoogLeNet and Inception, we witnessed the first act of architectural elegance, capturing multiple scales in a single glance. Highway networks and ResNet showed us that depth isn't an obstacle if you preserve identity. They gave networks a memory of themselves. From there emerged a family of refinement: wide ResNets, pre-activation, and ResNets, each asking what if depth wasn't alone. DenseNet took a bold stance: every feature matters, every layer contributes. Then came Xception, declaring decouple the what from the where, separating spatial and channel learning in a modular ballet. EfficientNet brought balance and harmony, proving that scaling isn't brute force, it's art. And finally, vision transformers carried the torch beyond convolution, reminding us that identity preservation transcends architectural dogma. Why philosophy? Because architecture is ideology in structure. Every design choice reflects a belief about computation, about cognition, and the future of learning itself. This atlas is your lens to decode those beliefs. Who this is for? If you are a beginner, this is your guided path through the towering giants of vision. If you are an engineer, then this is your toolkit of principles and blueprints. And if you are a researcher or AI philosopher, this is your archive of ideas that changed how machines see the world. In each chapter, we will unfold the historical context of the architecture, its philosophical essence, the technical innovations that backed it, and the legacy it left behind. All of this woven into a visual, structured, and intellectual stimulating map, your CNN architect mind. So join us not just to learn what these models do, but to ask why they were built this way. Because in deep learning, as in philosophy, form follows thought. Let's begin. Hello world. In this section, we will discuss LeNet 5. LeNet 5 is considered one of the very first CNN architectures in the world of deep learning. It was introduced in 1998. Its philosophy is based on learning hierarchy from pixels to characters. LeNet 5 introduced the convolution pooling pattern. This pattern is adopted by most of the CNN architectures in the world of deep learning. So you will notice that we have the pattern of convolution followed by a pooling. The convolution tries to detect features like edges, textures, shapes, colors, and the pooling tries to reduce the spatial dimensions. Why? Because it will reduce the risk of overfitting, enabling neural nets to learn shift invariant features. So our goal is to build models that learns shift invariant features that if we shift them in the other way, or if we shift them top or bottom or right from left, the model is still able to detect those features. So the model is still able to detect and identify those features directly from raw data rather than handcrafted. So rather than handcrafted kernels, rather than we specify the kernel values, LeNet introduced this concept of learnable kernels that will be initialized by random weights, by random values, and then with the help of backpropagation, so thanks to backpropagation and gradient descent algorithm, it will optimize and fine-tune those kernels values, those filters values, so the weights, the coefficients, the parameters, so that the model is able to represent our data in a better way. It symbolized the first step in automating visual representation learning. Okay, and then you can see here in this image, as you can see, we have the architecture of LeNet. So we have an input image of size 32 by 32. So the height is 32, and then the width is 32. Then we input that image to the architecture. The architecture consists of convolution. So we have a convolution layer that tries to detect edges, borders, boundaries, limits, ends, colors, different features from the image. For example, it tries to learn these features, tries to learn the angles of the A, tries to learn this edge, this line, this stripe, and so on and so forth. Then we pass this feature map. So we have here feature maps of size 28 by 28. Why? Because the convolution will reduce the size of the image. Then we pass these feature maps. So feature maps are the result of the convolution operation. The convolution operation results in a feature map. Then we pass those feature maps to a subsampling operation. Subsampling, at that time they were called subsampling, but now it will be referred to as max pooling or average pooling. But the broad term, the general concept is called subsampling. Subsampling is the operation that reduces or decreases the spatial dimensions so that the network can learn the most generalizable features, the most generalizable patterns, and get rid of that noisy features, get rid or remove those noisy and irrelevant patterns or features. Then we pass it to another convolution layer to learn more high-level features. Then we have another subsampling layer. So we have here, as you can see, we have the number of filters is 6. So we have here 6 filters, 6 kernels, and then the next convolution layer has 16 filters, so 16 kernels, and then we have a 10 by 10 as the feature map. So the feature map size is 10 by 10. Here, the feature maps after the first convolution and then the subsampling will output a 14 by 14 feature maps. So you'll notice that it will halves it. It will have the spatial dimensions. So it goes from 28 to 14. Why? Because subsampling halves the spatial dimensions. It reduces the size of the feature maps, and as you can see here, we have the height as 14 and the width as 14. Then we pass it to another convolution layer. This convolution layer will, as we said, it will also reduce the size from 14 to 14. It goes to 10 by 10, so it reduces 4 pixels from the height and from the width. And here we have more kernels, more filters. At the first convolution layer, we had 6 filters, but now we have 16 kernels, 16 filters. Each filter tries to detect a different pattern, different feature. Then we have, after this subsampling, we have fully connected layers. So we have here full connection. As you can see, we have flattened the feature maps and then passed them to a fully connected layer to learn more fine-grained features, more fine-grained and detailed features and patterns about the image. Then we pass it to another fully connected layer, another fully connected layer. As you can see, fully connection. Then we have here the last layer is the Gaussian connections that will produce output probabilities and classify into 10 different classes. Why 10 classes? Because we have 10 digits. Okay, so LeNet solved the problem of MNIST, which consists of digital numbers or digits. The philosophy in action. So LeNet's 5 foundational proof: hierarchical feature learning. So the feature learning was in hierarchical mode from pixels to patterns. LeNet 5 was groundbreaking because it automatically learned features hierarchies. Early layers captured simple shapes. So the first layers or the early layers captured simple shapes. Those shapes like triangles, like for example here we have a triangle-like shape. It learns some rectangular shapes. It learned simple shapes. Middle layers abstracted patterns like strokes. So the middle layers tries to learn more complex and more high-level features. Final layers combine those into digit-level concepts. So now the architecture is able, by reaching to the very last convolution layers, the architecture now is able to recognize digits as digits or characters as characters as whole, demonstrating a clear philosophical journey from raw pixels to meaningful characters. So the convolution neural network, the CNN architecture, slowly or gradually tries to learn from the image, starting from those simple hierarchies, simple features, moving towards learning the bigger and bigger or larger and larger features until it learned clear whole objects. Okay, so by the end of the architecture, the model is able to recognize, for example, a bicycle as a whole object by using learnable convolution kernels. So we use learnable convolution kernels, meaning the weights will be initialized randomly, and then with the help of the magical function of the magical algorithm backpropagation and gradient descent, it will optimize or fine-tune the weights inside these kernels and find the most suitable weights and values. So these kernels are learnable by using learnable convolution kernels plus pooled receptive fields. The receptive field is the region that the filter covers. So the region that the kernel covers is called a receptive field. It encoded spatial hierarchies without manual feature engineering. So we didn't need the manual feature engineering tasks. Number 2, shift invariance, seeing characters anywhere. So the model is able to see the characters, the digits anywhere in the image, whether it was at the top of the image or at the bottom of the image or in the middle, in the right, in the left, in the center. The model is able to recognize, to identify that this is a digit or this is a character. For example, this is a digit 9 in the image. The model is able to recognize this is a 9, whichever place it was placed on. Okay, so shift invariance, very important and significant concept in the world of image processing. LeNet 5 LeNet 5's use of convolution, so the convolution layer plus pooling achieved translation invariance, ensuring that a digit would be recognized regardless of its position in the image. This design mirrored the human visual cortical strategy of recognizing patterns regardless of small shifts. In practical terms, it gave the network the ability to generalize, recognizing handwritten digits even when centered imperfectly. Thirdly, we have end-to-end learning, minimal pre-processing. LeNet 5 was one of the first systems trained completely end-to-end from raw 32 by 32 pixels inputs to digit output via backpropagation, which is the algorithm responsible for optimizing the weights. This eliminated handcrafted feature extraction. So now we don't have that much handcrafted feature extraction. We are using now algorithms, for example, backpropagation and gradient descent that automate the process of feature extraction. Feature extraction is the process of learning the features, of extracting the features from images, and handcrafted filters. The model learned its own filters through optimization. Optimization is a really important process when training the model. So the model is trying to optimize its weights, its internal patterns, its knowledge to better represent the data, embodying the philosophy of automation. Then we have real-world impact, theory to practice. LeNet 5 wasn't just a lab experiment, it was deployed. It powered ATM check reading systems at AT&T NCR, processing tens of millions of checks daily by 2001. This dramatic real-world usage validated that the learned hierarchical features actually solved a complex real problem, and it solved that real problem, which is classifying the digits into themselves. For example, if you pass here an image that contains the, for example, number 2, then it will classify it as number 2, and so on. Okay, so it solved a real problem in the real world. So this is a real world impact. LeNet 5 wasn't just a lab experiment, it was deployed. It powered ATM check reading systems at AT&T labs. And then we have synthesis, philosophy confirmed. Philosophical pillars versus evidence in LeNet 5. Philosophical pillars, we have hierarchical abstraction. Okay, so there's a saying in deep learning, intelligence is abstraction. So when the neural network is able to learn the abstract generalizable features, then this is considered an intelligent model. So we have multi-layer convolution. We have multi-layer convolution that learns strokes / digits. Invariance and robustness. So when the model is able to detect that this is, for example, a digit 9, whichever place or wherever the place the 9 was placed, at the top, at the bottom, at the center, left, right, center, and the middle, then the model is considered robust. Okay, so invariance and robustness. Shared weights. The weights are shared. So in convolutional networks, the weights are shared, meaning the same set of weights inside the kernel is applied to the whole image. The same values, the weights are the same. When you apply a kernel on the image, then this kernel will contain the same numbers of weights, the same numerical values across the whole convolution operation. Okay, so shared weights. This is a really important concept in convolutional neural networks. Plus pooling for shift invariance. So the pooling operation helps us make our model more shift invariance. More shift invariance. Okay, so we have two important concepts, which is shared weights. So the weights are shared across the whole convolution operation. The kernel contains the same set of weights, the same set of numerical values across the whole convolution operation until the kernel finishes the image. It contains the same weights, so the weights don't differ. And we have the pooling operation that helps us make our models more shift invariance, which is if you, for example, translate the image or if you, for example, translate a digit along the x-axis or along the y-axis, also the model still able to recognize that this is the digit. Then we have self-land representations, gradient-based filters from pixels to characters. So we have this concept of gradient trained filters. These filters that are gradient land or gradient trained. Production viability, so massive deployment in ATMs, 20 million checks per day. Okay. Then we have a philosophical impact. LeNet 5 made manifested the ideal that visual perception can be land, hierarchical and automated, not hand designed. In doing so, it laid the bedrock for every modern CNN architecture that followed, from AlexNet through to ResNet and transformers. Featured paper, LeNet, 1998. It was introduced in 1998. And we have Yann LeCun. Yann LeCun is the author of LeNet architecture. Gradient in the paper, gradient-based learning applied to document recognition. And we have here Yann LeCun and ETL and et al. Proceedings to the IEE 1998, cited by thousands. This paper introduced the modern convolutional neural network capable of learning feature hierarchies directly from pixels. LeNet 5 made vision learning scalable and practical. And here we have this button. If you click on view, inline, then it will show us the paper. As you can see, gradient-based learning applied to document recognition by Yann LeCun and the remaining authors of the paper. And now if you scroll down, you can see that they try to solve this problem. We have here the same architecture. We have the character A, and we have a convolution layer, subsampling layer to reduce the spatial size. Then we have convolution layer to learn more high-level features, subsampling. Then we have 3 fully connected layers to classify for classification. And if you scroll down here, you can see that they have these digits, these numbers, 1, 2, 3. So they try to teach the model to recognize different numbers and different characters. As you can see, we have here digits, handwritten digits, size normalized examples of the MNIST database. So MNIST, if you don't know MNIST is short for Modified National Institute of Standards and Technology. So this is a MNIST database of digits database, and you can read through that in your own free time. Okay, so I'll let you read that in your own time. And now we will move onto AlexNet. AlexNet philosophy is make deep feasible. AlexNet proved that depth matters, but only with GPU power. GPU is short for graphical processing unit. These units accelerate the computing, accelerate the computations. ReLU activations, so ReLU is short for rectified linear unit. ReLU activations allows the model to learn complex nonlinear relationships. Dropout is a regularization technique. It's a regularization technique that allows a model to reduce the risk of overfitting. And data augmentation. So we have 3 important pillars in AlexNet. AlexNet is the first architecture that used GPUs or utilized GPUs to train the model. Also, they have used ReLU activations, ReLU functions to help the model learn complex nonlinear correlations. And also we have dropout, which is a regularization technique that helps the model to reduce the risk of overfitting. And the author who invented dropout is Geoffrey Hinton. And we have data augmentation. Data augmentation is a set of techniques that helps diversify a training dataset so that the model can learn robust and generalizable features. It broke the computational barrier, showing deep learning could outperform prior methods and sparking the modern AI renaissance. And here, as you can see in the image, we have AlexNet architecture. So we have here 3 color channels. We have the red channel, the green channel, and the blue channel. So here you can see we have 3 color channels. As you can see, the height of the image is 227 by the width is 227, and we have 3 color channels, which is the usual color channels that an image used to represent. So you have the red channel, the green channel, and the blue channel. Then we pass these channels, these dimensions, or this image to a convolution layer, and this convolution layer has a kernel size 11 by 11. So the first convolution layer uses a kernel size of 11 by 11. The height is 11 and the width is 11, and the stride size is 4. So each kernel moves by 4 pixels. And as you can see, now the height is 55 by the width is 55, and they use, so you can see the height and width now are reduced. So the convolution layer reduces the height and the width, and it has 96 filters or 96 kernels. Then we pass it to another set of convolution layers and also max pooling layers, and we end up with these fully connected layers, and then classify into 1,000 classes. Why? Because they trained AlexNet architecture on the ImageNet. ImageNet has 1,000 different classes, 1,000 different objects, and the number of parameters inside this model is 60 million parameters. So we have 60 million total parameters inside the model. What are the parameters? The parameters are the kernel's weights or the filter's weights, and also the biases. So the internal configurations inside the model is called parameters, whereas the external settings of a model are called hyperparameters. You as a machine learning engineer defines the values for those hyperparameters, whereas the learning process defines, or when the model learns, it tries to find the best parameters, tries to find the best values for those parameters. Now if you go down, philosophy in action, AlexNet's foundational proof, depth with practical feasibility. So we have the first pillar is the depth. So it's considered a deep model. As you can see, we have here deep architecture. Okay, so the depth is feasible with practical feasibility. Core idea: before AlexNet, deep networks underperformed due to vanishing gradients and overfitting. Vanishing gradients is a common problem in machine and deep learning. What is vanishing gradients? Vanishing gradients are when the gradients are the values that the algorithm backpropagation calculates. When the gradients become too small near zero at the end of the architecture, so that the model isn't able to learn. The model can't learn well. So the model is called, or the model is suffering from the vanishing gradient problem. And overfitting. Overfitting is when a model performs really well on the training data but struggles with new unseen data. So here the core idea is that before AlexNet, deep networks underperformed due to vanishing gradients and overfitting. AlexNet broke through by showing that introducing depth, 8 layers. So we have 8 layers inside the architecture. We have 5 convolutional layers and we have 3 fully connected layers. So we have 5 convolution layers and 3 fully connected layers. Okay, these are fully connected layers, and as we said, these layers do feature extraction, the convolution layers, but the fully connected ones do classification. It classifies into some number of objects or classes. So introducing depth 8 layers is feasible and beneficial with the right tools. Empirical evidence. AlexNet achieved 15.3% top 5 error on ImageNet, as a staggering 11% improvement over the runner-up. Demonstrated depth could yield measurable gains across a massive dataset. So AlexNet demonstrated that depth could yield measurable gains across a massive dataset. Also, the second pillar is GPU computing. As we said, GPU is short for graphical processing unit. These units, or these processor units, accelerate the computing operations, accelerate the computations, and also accelerate the operations inside the network, removing the compute barrier. Core idea: leverage GPUs to train deep networks at scale, turning theoretical depth into practice. So they turned the theoretical depth into practice. Evidence: training conducted on 2 NVIDIA GTX 580 GPUs, each with 3 gigabytes VRAM over 5 to 6 days. So it took 5 to 6 days to train the model. Emergence of GPU frameworks like CUDA ConvolutionNet enabled this GPU scale experimentation. Thirdly, we have ReLU activation. And as we said, ReLU is an activation function that helps the model to learn nonlinear complex correlations, to learn nonlinear complex relationships, faster training, and vanishing gradient fix. So if you go to neural network playground to see this phenomena in action, and if you go, so we have here a neural network. As you can see, we have a simple neural network, and here we have the problem as classification. So we have to choose problem type as classification. If you choose regression, you will get here regression data. But now we have to choose classification because we want to classify data. And here, data, as you can see, which dataset do you want to use? So here they are asking you which dataset do you want to use. You could use this circular dataset, you could use this dataset, you could use this dataset, any dataset you can choose from. I will choose the circular one. Then you can also play around with the number of layers. You can go as many layers as you want, or you could decrease it. I will choose here 3 layers. So let's use 3 hidden layers, and let's increase the number of neurons to 5 neurons in each layer. Now we have 5 neurons, 5 nodes in each layer, and now if you want to train the model, just click on this. You can play around with the activation. The important thing in here, the important concept is that if we choose sigmoid, let's start with the sigmoid activation function and train this model. And let's set the learning rate as the default, which is 0. For example, 0.1. And now let's train the model. It's now trying to separate these 2 classes. As you can see, the model now is trying to learn to separate these 2 classes. So here you can see that the process is really slow. You could also accelerate the learning rate to make it, for example, 0.03 and train the model. So it will take time. But now if we choose tanh activation and retrain the model, you can see that tanh is faster, and it took about 65 epochs. But let's try ReLU. Now let's try to train this model using the ReLU function. Now let's train. So from the first 20 epochs, the model is able to converge faster, to separate, or to draw a boundary or a decision boundary between the 2 classes. So here we infer that ReLU activation leads to faster training. So if you choose ReLU activation, it leads to faster training. Also vanishing gradient fix. It fixes the problem of vanishing gradients. So core idea: replace saturating functions like sigmoid and tanh with ReLU to mitigate vanishing gradients, allowing effective backpropagation through deep layers. So here we can see that ReLU is able to separate or to classify the 2 classes in about the first 20 epochs. Whereas if we choose sigmoid, you can see the model isn't able to classify. Now we have reached 100 epochs and the model is still not able to classify. Even if you increase the number of layers here, you can increase it, and then you can increase the number of neurons, then you can go train the model with sigmoid. Now even if we have more layers, but with sigmoid, the model is still not able to classify between the two classes fastly or quickly. Evidence: layer outputs modeled with ReLU trained several times faster than Tanch and sigmoid. So this is a really important concept. Enabled deeper architectures by preserving gradient flow. And now if you go here, dropout. Dropout is a regularization technique that helps the model to regularize itself by a neural level. And dropout is really important concept. Why? Because we try to build neural networks that are less dependent. Our goal in machine learning, in deep learning, is to build models that are less reliant, that are less dependent. So we try to teach the model to be less reliant on specific neurons, on specific nodes. Because the other side, if the model is too dependent, too reliant on specific neurons, then the model will not be able to generalize across many different features, across many different input space. So controlling everything with deep nets. Core idea: introduce neuron level regularization to make depth less prone to overfitting. So we are making the depth less prone to overfitting. Evidence: dropout at probability 0.5. So 50% of the neurons, 50% of the units are dropped out, are dropped off, is in fully connected layers, prevented co-adaptation. So if you use dropout at probability 0.5 in fully connected layers, this prevents the co-adaptation. Co-adaptation is when a neuron fixes another neuron's error, aiding generalization. So we are preventing the problem of co-adaptation. Modern analyses confirm dropout remains one of the most effective methods for reducing overfitting. So dropout is the king of all, or the king between all other regularization techniques or regularization methods. Again, to revise, dropout is a technique in machine learning, is a regularization technique in machine learning, in deep learning, that helps models to be less reliant, to be less dependent on specific neurons, on specific nodes. How? By dropping out several neurons or several units by a percentage you have to choose. So this percentage, you as a machine learning engineer, as a machine learning engineer, you have to choose the probability. If you choose probability, for example, 0.2, then 20% of the neurons will be dropped out. Then 20% will be dropped out. If you see this image here, dropout regularization in machine learning, and if you go to images, you can see here this image. Yeah, we have these neurons dropped out. So this standard neural net, and we have here after applying dropout. After applying dropout, some of the neurons in the input layer and in the hidden layers will be dropped out, will be turned off, will be disabled. Why we do this? We try to build a new smaller sub-network inside the whole network that is capable of learning by itself. So then we average all the powers of all sub-networks. This is one. Two, also dropout helps to make neurons learn by themselves, not dependent on each other. So all neurons have the same chance of learning, not as neurons having more chance of learning and the other have low chance of learning. And thirdly, by doing this, we prevent or reduce the risk of overfitting. And overfitting is when a model is performing really well on the trained dataset but struggles with new unseen data. Data augmentation is one of the most important pillars in AlexNet. scaling data to model complexity. So when you do data augmentation techniques, when you apply data augmentation, you are scaling the data to the model complexity. Core idea: use cheap online augmentations to expand the dataset, providing data to match model depth. And here you can see evidence. AlexNet used on-the-fly transforms, so transforms happening when training the model. So when we are training the model, these augmentations are being generated, or these transforms are being applied, which is random crops, flips, and PCA-based color permutations, effectively expanding the dataset by a factor of 2048, of about 2048. Later research shows augmentation alone can outperform other regularization techniques. Okay, so this is an important aspect. Summary: how AlexNet validated its philosophical pillar. Here we have philosophical pillar and technical innovations. Philosophical pillar: we have deep matters. So we have the aspect of depth. As we said, AlexNet is considered a deep model. It is said that AlexNet is the first deep learning model in the world. So it's considered a deep model. And as we said, the philosophy here, make deep feasible. AlexNet philosophy is make deep feasible. And if you go down here, we have 8 layers CNN. So we have 5 convolution layers followed by 3 fully connected layers. Top 5 error 15.3%. Here we have evidence and impact. Top 5 error about 15.3% versus 25%. Modern deep learning era begins. So we have modern deep learning era begins. We have compute matters. So the compute here matters because we have a deep model. The computation will increase. So they solved this issue with the GPU parallel training. So they leveraged GPU. They utilized GPUs. Feasible training in 1 week on dual GTX 590s. Then we have nonlinearity matters. They applied the nonlinearity learning by using ReLU activations. Through using ReLU activations, as we said, ReLU is a activation function that helps the model to learn complex curved lines, help the model learn complex correlations inside the images, inside data. Here we have faster convergence. Also, they achieved faster convergence than tanh and sigmoid, because tanh and sigmoid are really suffering from the vanishing gradients flow problem. So we apply ReLU to mitigate that problem. And now we have regularization matters. So we have a technique called dropout. As we said, dropout is a regularization method that helps the model to learn generalizable patterns, helps the model to be more effective and less and learn less redundant features. And augmentation avoided overfitting, enabled depth. Philosophical takeaway: AlexNet operationalized the concept that depth unlocks powerful visual abstractions, but only when paired with modern compute. So GPUs, we have modern compute, efficient nonlinearities by using ReLU, and robust regularization. Its success was the first real demonstration that CNNs could scale meaningfully with data. So CNNs now are able to learn complex images, to learn complex objects inside images, and hardware to surpass classical vision methods, triggering the deep learning revolution still unfolding today. Featured paper, and we have here the paper, AlexNet. AlexNet, by the way, was introduced in 2012. So this was the year that they introduced AlexNet in. And here we have the author Alex Krzyzewski with Ilya Stuskover and Geoffrey Hinton. Geoffrey Hinton is the godfather of AI. And here you can read that they achieved top 5 error of about 15.3%. Landmark deep CNN paper. AlexNet cracked the ImageNet barrier, showing that with enough depth and with enough GPU power and regularization, deep learning could scale and surpass all prior vision methods. And you can see here, if you click on view inline. This is the paper that they introduced AlexNet in. ImageNet classification. ImageNet is a large-scale image database consisting of 1,000 classes. ImageNet classification with deep convolutional neural networks. And you can read through that in your own time. Feel free to read and explore. Always explore. And you can see here the architecture. We have here the architecture of AlexNet. The first convolution layer here. We have stride 4. And they inputted these images 2 to 4 by 2 to 4 by 3 color channels. And then we have max pooling layer. As we said, max pooling is an important layer in CNNs, and the purpose of max pooling is to reduce the spatial size, to reduce the spatial dimensions, so that the model learns robust features, learns the important features, the significant features, and also get rid of those irrelevant, noisy features. So max pooling also reduces the risk of overfitting, and you can read through that, and you can see here they visualized the representations. These are the representations. So here you can see convolutional kernels of size 11 by 11 by 3 learned by the first convolutional layer on the 2 to 4 by 2 to 4, which is 224 by 224 by 3 color channels input images. So these are the representations, the edges, the corners, the angles, the lines that the convolution layer learns, and you can scroll down to explore all of this model. Okay, so now we have finished AlexNet. Let's move on to VGG. Now let's discuss VGG. So VGG is a convolutional neural network, and its philosophy is from pixels to perception. VGG embraced simplicity and depth using repeated 3 by 3 convolution layers to focus on hierarchical abstraction rather than complex modules. It taught the community that depth with uniformity could outperform manually engineered feature structures. And as you can see here, we have the convolutional neural network VGG architecture. So first we input an image of height 224 and width 224 and has 3 color channels. We input it to the first convolution layer. Then this convolution layer learns to detect different features and pass it to another convolution layer. Then we have a max pooling layer. As you can see, the red layers are max pooling layers, max pooling, and then we have a convolutional layers here, convolution, then we have max pooling. So we have this kind of trend, we have this kind of pattern. Two convolution layers followed by a max pooling. Then we have 2 convolution layers followed by a max pooling. Then we have 3 convolution layers followed by max pooling. Then we have 3 convolution layers followed by max pooling. Then at the last we have 3 convolution layers followed by 1 max pooling. Then we have 3 fully connected layers. So this is the overall architecture. Then we classify into 1,000 different classes because we are dealing with ImageNet. ImageNet is consisting of 1,000 different categories, 1,000 different classes. So when they tried to train VGG, they trained the VGG architecture on ImageNet dataset, and the ImageNet contains 1,000 classes, 1,000 categories. So they have to have 1,000 neurons in the last layer. Philosophy in action. How VGG proved from pixels to perception. Uniform depth. So this is an important concept in VGG. They have uniform depth, embracing simplicity. VGG structured its entire convolutional backbone using only 3 by 3 filters. Unlike AlexNet, if you recall, we said that AlexNet consists of an 11 by 11 kernel size. So they have a kernel size of 11 by 11. But VGG emphasizes uniformity or leverages uniformity. So we have uniform depth. VGG structured its entire convolutional backbone using only 3 by 3 filters alongside max pooling, stacked up to 19 layers. So they had 19 layers. Recall that AlexNet consists of just 8 layers, 5 convolutional layers and 3 fully connected layers. But here we have 19 layers, so deeper. Now we have a more depth model instead of mixing varied filter sizes or complex blocks. So VGG, instead of mixing varied filter sizes, they used a uniform filter size. They used the same filter size across the whole architecture. So across all this architecture, every single convolutional layer is a 3 by 3 kernel size, or has a 3 by 3 kernel size, or filter size, or you could say window size. This uniformity allowed the network to build hierarchical features smoothly, from edges in early layers to textures and patterns, and finally to object components, to whole object components in deeper layers. Empirically, this simple but deep design outperformed models like AlexNet, which is a nice thing. So VGG outperformed models like AlexNet and GoogLeNet in ImageNet. This is a short for I, ImageNet, L, large scale, S, scale, V, visual, so visual, R, recognition, C, challenge. So ImageNet large scale visual recognition challenge 2014, because they introduced this nice architecture in 2014. Okay, so here we have VGG introduced in 2014. Now if you go down here, okay, as we said, empirically, this simple but deep design outperformed models like AlexNet and GoogLeNet in ILSVRC 2014, because they introduced it in 2014, proving that simplicity plus depth equals strong abstraction. So this VGG architecture is strong in capturing the abstraction, the representation abstraction, the representation learning. Okay. 2, we have efficiency in parameters and competition. Also, this architecture is efficient in counting the counting the parameters, or in using the parameters. 2 stacked 3 by 3 convolutions achieve an effective receptive field. And as we said, this is an important concept in CNNs. Always you will hear, when you deal with CNNs, you will hear receptive fields. Receptive field is the region that is covered by the filter, or that is covered by the window. This region or this area is called a receptive field of 5 by 5 with fewer parameters, 18c square, and we have 25 versus 25c square, reducing overfitting. So when you have less parameters, that leads to a less model that is less prone to overfitting. That leads to a model that is less prone to overfitting. Okay, so reducing overfitting risk and boosting efficiency. So they have boosted efficiency. This parameter saving insight allowed VGG to go deeper. So this feature, which is parameter saving, they saved a massive amount of parameters. This parameter saving insight allowed VGG to go deeper without explosive resource usage, because the more parameters, that means more competition. Every single parameter increase equals more competition, because this parameter needs to be adjusted, needs to be fine-tuned. So you have to do some kind of mathematical operation. But when you decrease the amount of parameters, when you decrease the amount of parameters and internal weights, that this leads to an efficient model, a fast computing model, affirming that simple repeated modules can surpass bespoke heavy counterparts. Hierarchical feature composition. So this is an important aspect. Academic analyses confirmed that deeper layers of VGG, the deeper layers, so here we have this deep layers, we have this convolution layer, this convolution layer, this layer, and also these layers. So these convolution layers, the deeper ones here, deeper layers of VGG capture high level semantic concepts. So the semantic meaning or the semantic concepts inside an image. So this bicycle refers to a bicycle. So now the model is having a semantic meaning of what a bicycle is without being explicitly told what cats or dogs look like. So the model is able to recognize. This architecture is so powerful. It is able to recognize objects as objects, components as components, not as LeNet. LeNet was only just able to recognize strokes, lines, digits, but this architecture is able to recognize cats, dogs, dolphins, etc. So this demonstrates the philosophy. Raw pixels transform through layers into perceptual representations. So we have this concept, representations. Representations are the learned features flowing naturally through depth and simplicity. Empirical success, benchmarks and style. VGG achieved remarkable results. This was a remarkable architecture in the world of deep learning. VGG. VGG is short for Visual Geometric Group. Okay, so VGG achieved remarkable results in ImageNet ILSVRC 2014, a strong runner-up, validating that depth-focused uniformity. So the depth-focused uniformity competes at the highest level. Its architecture also became the backbone of fast RCNN, which is region convolutional neural network. So this is a beautiful thing. Its architecture also became the backbone of fast RCNN and neural style transfer, influencing downstream tasks in detection, segmentation, and generative modeling, providing its hierarchical features are widely effective. So proving its hierarchical features are widely effective. And here we have philosophical summary. If you see here, philosophy pillar versus VGG's implementation and evidence. Philosophy pillar, simple. So if you see here, we have a simple architecture. So we have just a combination of convolutional layers, such as this. We have a convolution layer, we have a second convolution layer, then we have some max pooling layer. And as we said, max pooling is a type of layer in deep learning that reduces the spatial dimensions, that reduces or decreases the spatial size. Why? Because we want to teach the model generalizable features, to teach the model the most significant features, the most prominent, the most important features, and get rid of those less important, irrelevant, noisy features. Then we have another set of convolution layers. We have two convolution layers, then another max pooling to reduce the size, to reduce the risk of overfitting, to get rid of those noisy features in the image. Then we have three convolution layers. So this pattern is simple. We have a simple architecture, not as complex. Then simple, uniform, and also we have some uniformity. We have uniformity in the architecture. As you can notice here, we have some kind of pattern. So we have two conv layers, a max pool layer, two conv layers, a max pool layer, and then three conv layers, one max pool, three conv layers, one max pool, three conv layers, one max pool. Unlike AlexNet, AlexNet doesn't have uniformity. If you recall AlexNet, we don't have here, we just have 5 convolution layers in a random way, then we have fully connected layers. We don't have uniformity in the architecture, but VGG emphasized the uniformity aspect. So uniform modules stacked 3 by 3 convolutions. So they used a 3 by 3 as the kernel size. So they have a 3 by 3 as the kernel size. Then we have here consistent across depth. Parameter efficiency. So the efficiency in parameter. Smaller kernels achieve larger receptive fields efficiently. Always remember, smaller kernels achieve larger receptive fields efficiently. Hierarchical abstraction. Deeper layers learn object level features. This is a significant note about VGG. The deeper layers about VGG, or the deeper layers in VGG, learn not just lines, not just strokes. They learned object level features without supervision. Benchmark excellence and influence. Strong ILSVRC performance widely used in transfer tasks. So as you can see here, we have widely used in transfer learning tasks. Transfer learning is the art of taking a previously pre-trained model and applying it on your own task, to your own task or use case. Philosophical takeaway: VGG validated its philosophy by showing that simple modules stacked deeply can yield sophisticated perception, a message that shaped the next wave of CNN, convolutional neural networks design, and became a staple in computer vision. Featured paper: we have this paper of VGG. As you can see, this is the author of VGG, Karen Siminian, and also Andrew Xception. So these are the two authors of VGG Architecture. VGG, very deep convolutional neural networks. So this is the title of the paper: very deep convolutional neural networks for large-scale image recognition, and one of the most influential CNN architectures to date. VGG's power come not from architectural complexity, but from elegant repetition. It proved that depth through simplicity could build perception from pixels, could build perception from just raw pixels. And you can view the paper here. View inline. We have this paper of VGG, very deep convolutional neural networks for large-scale image recognition, by Karen Siminian and Andrew Xception, Visual Geometry Group. So VGG, Visual Geometry Group, Department of Engineering Science, University of Oxford. It came from the University of Oxford, and here you can read. Feel free to read through this paper in your own time. You can explore more how many parameters they used, how they achieved this kind of architecture. Okay, so now we have finished the VGG. Let's move on to GoogLeNet, Inception. Now we will discuss GoogLeNet, Inception. So Inception, or GoogLeNet, is a convolutional neural network, and its philosophy is seeing multiple scales with one glance. So we are seeing, with this architecture, we are seeing multiple different scales with one glance. Inception networks introduced parallel filters, 1 multiplied by 1, so the kernel size is 1 by 1, and also 3 by 3, 3 rows by 3 columns, and the window size also 5 by 5. So we are using 3 different sizes: 1 by 1, 3 by 3, and 5 by 5 within modules, enabling multi-scale feature capture while controlling computation with bottleneck 1 by 1 convolution. So you can imagine, if we used all these different filter sizes, what the computation would look like. So we are also managing or controlling the computation with bottlenecks 1 by 1 convolutions. It solved the problem of scale awareness and efficiency in one leap. And as you can see here in the image, we have the nice architecture of GoogLeNet. As we said, the idea was to allow the network to perceive visual information at various receptive field sizes simultaneously, capturing both fine details and global patterns without bloating the computational cost. How the architecture aligns with the philosophy? Well, Inception modules see multiple scale feature extraction. So we are here learning multi-scale feature extraction. Each Inception block, as you can see, each Inception block contains parallel branches that process input using 1 by 1 convolutions. So 1 multiplied by 1 convolutional layers for dimensionality reduction, and also 3 by 3 convolutions, mid-level features, to learn medium level features, mid-level features, and also we have 5 by 5 convolutions, larger contextual features. And we also have 3 by 3 max pooling to maintain spatial invariance. And as we said, spatial invariance are the features that are generalizable. So whichever the place that, for example, the airplane was directed towards, the model still able to recognize that this is an image of airplane. So we want to teach the model invariant features, spatial invariance. These branches are then concatenated depth-wise, effectively combining features from multiple spatial scales. So as we said, these branches are then concatenated depth-wise, effectively combining features. So we need to combine features from multiple spatial scales. As we said, we have multiple scales, 1x1 convolutions for dimensionality reduction, and we have 3x3 convolutions, mid-level features to extract mid-level patterns, and we have 5x5 convolutions for larger contextual features, or to learn larger objects, larger components. So these branches are then concatenated depth-wise, effectively combining features from multiple spatial scales. Hence, the philosophy seeing multiple scales with one glance. One glance refers to in parallel or simultaneously. And also, they leveraged 3x3 max pooling to maintain spatial invariance. 1x1 convolutions, bottleneck for efficiency. So they used a bottleneck technique, which is a 1x1 convolution for efficiency. The red blocks labeled 1x1 convolution, so these layers are bottlenecks, act as bottlenecks to reduce the number of channels before applying the heavier 3x3 and 5x5 convolutions. This dramatically reduces flops, floating point operations, and parameter counts, parameter amounts. So this technique, bottlenecks, reduces the amount of parameters and also reduces the flops operations from about 112 million operations to about 5.3 million per branch in the original Inception paper. Effect enables deep architectures without the prohibitive compute costs seen in VGG. Thirdly, we have deep yet narrow efficient depth. So this architecture is deep but yet narrow efficient depth. GoogLeNet has 22 layers deep. So GoogLeNet architecture has 22 layers deep, but thanks to the Inception design, it avoids parameter explosion. It avoids parameter bloating. VGG 19 had 144 million parameters, whereas GoogLeNet achieved better accuracy with only 6.7 million parameters. So VGG 19 had 144 million parameters. GoogLeNet achieved better accuracy with only 6.7 million parameters. And we also have auxiliary classifiers, early supervision. So we have two auxiliary classifiers, which are smaller branches that end in fully connected plus softmax layers. So fully connected is a densely connected layer or fully connected layer where we have nodes or units or neurons. Each node is connected to every node in the second layer. Fully connected layers. Plus softmax. The softmax layer is an activation function that converts the raw scores, the raw logits, into probabilities. These provide intermediate gradient flow. So the purpose of these auxiliary classifiers is to provide intermediate gradient flow, helping train deep networks. Second, act as a kind of regularization, discouraging overfitting in early layers. So it discourages overfitting in early layers. Overfitting is a problem or issue, is a common issue in deep learning, and happens when the model is training really well or is performing really well on the training data, but struggles with new unseen data. And then we have global average pooling, compact output. So instead of using huge fully connected layers at the end, GoogLeNet introduced global average pooling before the final softmax. This eliminated 90% plus of the parameters from dense layers and improved generalization. Okay, and then as a revise, As we said, we have Inception modules, contribution to CNN advancement, multi-scale receptive fields in parallel. So we in the GoogleNet we applied multiple scale receptive fields in parallel simultaneously in one glance, applying 3 different scales, 3 different filter sizes, 3 different kernel sizes, 1 by 1, 3 by 3, 5 by 5. 1 by 1 convolution, learn detailed, fine-grained details, very local details. 3 by 3 convolutions, learn mid-level features like edges and textures. 5 by 5 convolutions, learn larger contextual features. And also we have a 3 by 3 max pooling to learn feature invariance. Then we have 1 by 1 bottlenecks. These are bottlenecks techniques for efficiency without loss of expressive power. And we have auxiliary classifiers, early deep supervision, better gradient flow. Also we have global pooling. Global pooling is for compactness and also regularization without dense layers. And this architecture is known for its reduced parameters, 6.7 million parameters, outperformed larger models, for example VGG. So as a conclusion, philosophy to practice, GoogleNet or Inception redefined what deep could mean, not just by stacking layers vertically. So not just blindly stacking layers vertically, but architecting smart, parallel, efficient pathways that mimic the flexibility of human perception. It proved that architectural design, not brute force depth or size, was key to progress in deep learning. So here, as we said, philosophy in action, how Inception proved its core idea, parallel multi-scale feature capture. Idea, rather than choosing a single filter size, so as in AlexNet and VGG, we have like 3 by 3 or 5 by 5. In Inception modules or Inception blocks, Inception performs 1 by 1, 3 by 3, 5 by 5 convolutions alongside pooling in parallel within each module. Verification, the D2L dive into deep learning textbook shows first 3 branches use convolutional layers with window sizes of 1 by 1, 3 by 3, and 5 by 5 to extract information at different spatial sizes. Philosophical proof, by learning across scales simultaneously, Inception embodies seeing multiple scales with one glance. Letting the network choose which scale best represents a feature. So now we are applying, or in GoogleNet, we are applying 3 different kernel sizes, 3 different window sizes, and we let the network choose which scale, which filter size, which scene best represents a feature. Efficiency via bottleneck 1 by 1 convolutions. So they applied 1 by 1 convolution layers as bottleneck techniques. Idea, to prevent explosion in compute and parameters. So in both, in compute and also in parameters. Inception places 1 by 1 convolutions before the expensive 3 by 3 and 5 by 5 operations, reducing channel depth. So by using this bottleneck technique, we are reducing channel depth. Evidence, a dramatic drop from 112 million operations to about 5.3 million for a single branch. Philosophical proof, this action preserves multi-scale perception. Multi-scale perception is we are using 3 different window sizes without inflating resources. So this action, which is bottleneck, preserves multi-scale perception without inflating resources, illustrating that efficient scale awareness is as vital as capturing scale itself. Staying deep yet trainable via auxiliary loss. Idea, GoogleNet introduced auxiliary classifiers midway to combat vanishing gradients. So as we discussed, vanishing gradients. When the architecture goes deeper and deeper, it suffers from the vanishing gradients problem or the vanishing gradients issue. This issue happens when the gradients become too small or become near zero at the end of the architecture, so that the network would not be able to learn or would struggle to learn. So here, the auxiliary classifiers idea, GoogleNet introduced auxiliary classifiers midway to combat vanishing gradients and improve convergence. Evidence details that these linear softmax classifiers were weighted and removed after training to stabilize learning. Philosophical proof enabling deeper architectures to learn localized multi-scale representations reliably, reinforcing that seeing better scales depends on strong training dynamics. Empirical performance, multi-scale philosophy validated achievement, GoogleNet or Inception version 1. We have multiple different versions. We have Inception version 2, Inception version 3. So Inception version 1 achieved top 5 error of 6.7% on ImageNet large-scale visual recognition challenge 2014. Significant improvement over both AlexNet and VGG. Efficiency, it used 12x fewer parameters than AlexNet and VGG, proving that multi-scale perception can be efficient. So now we have a lesson that multi-scale perception allows the network to learn by letting the network choose which filter size, which perception size best represents the features. So here proving that multi-scale perception can be efficient. Philosophical impact, it wasn't just deeper, it was smarter in how it allocated depth and computation across scales. So the architecture here is smarter, not as just blindly stacking layers vertically, but it is smart in how they architect the architecture, how they built the architecture. Philosophical summary, pillar, multi-scale feature perception, implementation, parallel, 1 by 1, 3 by 3, 5 by 5, and pooling. Philosophical significance, captures varied visual information in one module. Computational efficiency, bottleneck 1 by 1 convolution reduces cost. Efficiency doesn't mean scaling alone, it means intelligent scaling. So they used intelligent scaling techniques like bottleneck 1 by 1 convolution. Trainability of depth, auxiliary classifiers stabilize gradients, stabilize gradient flow. Depth needs guardrails to retain multi-scale perception. Performance validation, SOTA is short for state-of-the-art accuracy. So they achieved state-of-the-art accuracy at reduced resources. So here we have a great lesson that we have, which is the beta lesson. As you can see, the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation and ultimately the most effective and by a large margin. So as here we can read, the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation and ultimately the most effective and by a large margin. So we have three important aspects in deep learning, which is we have three important aspects in machine learning is how fast is your model? How fast is your model? So fastness. 2, we have the size of the model. So how big is your model? And thirdly, we have how performant is your model. We always want the fastest model as possible. We always want to reach the fastest model as we can, with also the smallest model as possible. Why we want the smallest model? Because models, we need models to fit in mobile devices, in tablets, in computers, in servers. So we need the models to fit across different computing capabilities, across different computing powers. So we need small models, so less parameters, but also yet performant models with high accuracy rate, and also to be fast models. Because what is the purpose of a model that, for example, takes half an hour to predict? So we need fast models, we need really performant models, so really high accuracy models, and also we need small models to fit across devices. For example, we have an architecture that is called MobileNet. MobileNet, this is the CNN architecture that is suitable for mobile devices. For example, in drone devices and different devices that capture images. So performance validation, state-of-the-art accuracy at reduced resources. Philosophy proven by real-world performance. Philosophical takeaway: GoogleNet's innovation was to realize that vision happens at multiple scales and to capture this in a single module intelligently and efficiently without sacrificing depth or performance. It showed that scale awareness and efficiency can coexist and that complexity can be elegant. And here we have a comparison between the different types of pooling techniques in CNNs. We have feature aspect, we have also max pooling. So we have the first type is max pooling, and we have also average pooling. As you can see, we have average pooling, and we have global max pooling, and we have global average pooling. Let's compare them in a quick mode. So definition: max pooling takes the maximum value in each batch. So if we go to CNN Explainer, you can see that we have here a layer that is called max pooling. And when you go to this layer, which is max pooling, let's take a highly activated image, for example this image, you can see that we have a patch. This is a kernel or a filter. You can see that I am moving now a kernel. I am moving a kernel or window. This is called a window or filter. This filter, the region that gets covered, the region or the area that gets covered by this kernel is called receptive field. This receptive field, also known as patch using this syntax, patch. So the max pooling takes the maximum value across the batch. So we have the max value here 1.48. If you go here, the max value is 1.87. So we are taking the max value across the batch, or from a batch, just from a single batch, and then the result would be another feature map, would be another matrix. Okay, so you have to know that max pooling takes the maximum value, takes the largest value, takes the biggest value in each batch. Average pooling takes the average of values in patch. Also the same idea, but here we have max pooling. Assume we have average pooling. It will do the same thing, but it will take the average. It will sum all these numbers and divide them by 4, by the number of values. Then it will give me the average. But what about global? Why do we have global? And it's important to understand global max pooling, because here, as we said, in GoogleNet they leveraged the global max pooling. As you can see here, as we said, they leveraged the global max pooling. Here they used global average pooling because they want to pass to the fully connected layers. So let's now read about global max pooling and also global average pooling. Global max pooling takes the maximum over entire feature map. Over entire feature map. Feature map is an important concept in CNNs. A feature map is the result of a convolutional layer. So the last convolutional layer here, the last convolutional layer will produce or will result in a feature map. We will pass this feature map to a layer which is global max pooling or global average pooling, and it will take the max or average across the entire feature map, not just across one batch. As we said in here, if you go to this image, it will take the maximum value across this batch. Here you can see we have this kernel size, and it takes the max value across a batch. Global average pooling takes the average over entire feature map. Goal or effect? Well, max pooling captures most salient features, strong activations. It takes the strong activations, but average pooling smooths features, captures overall trend. Global max pooling captures strongest global activation, and global average pooling captures overall global response. And here we have the window size. Typically, 2 by 2 or 3 by 3, because typically max pooling, okay, max pooling is common to be 2 by 2 or 3 by 3. It's not common to see, it's rare to see a larger window size in max pooling. The same thing for average pooling, typically 2 by 2 or 3 by 3. And global max pooling, you don't define any window size. You don't define, here in global max pooling layers, when we use global max pooling layers, we don't define the window size. It is the same as feature map size. Also the same thing with global average pooling, same as feature map size. The stride usually equals window size. So we have a common practice is to uniform the stride size with the window size of the max pooling. So usually equals window size, non-overlapping. And average pooling the same. Here, not a number, entire feature map pooled to one value. So the entire feature map pooled to one value. And here global average pooling is not a number. Output shape, well, you can imagine that here the output shape is what? Is a matrix. Is a matrix or is a feature map. A feature map is a matrix that contains the activations. It is also called feature map or activation map. So these are the activations, the most important features, the most salient parameters. Okay, so if you go back here, we have output shape, smaller spatial dimension, downsampled. The average pooling same, reduced height and width. And here we have one value per channel. So when we use global max pooling, we get one value per channel. So it gets rid of the height and width, making the height as 1, making the width as 1, but the number of channels, we have one value per channel. And here we have one value per channel in the global average pooling. Well, parameters land, we don't have any learnable parameters in all of these layers. So there are layers that we don't have any learnable parameters. For example, ReLU layers don't have any learnable parameters. We don't have anything learned in ReLU layers. ReLU layers just take the maximum value between 0 and the value. If the value was a negative value, if you take this image, we have some values that are by negative, so we choose 0. And if the value was positive, then we will take the positive value. So ReLU doesn't have any learnable parameters. Also max pooling, average pooling, global max pooling, global average pooling, we don't have any learnable parameters. Parameters land, no. Sensitivity to outliers, well, max pooling high. Max pooling is so sensitive, highly sensitive to outliers, focuses on extreme values. Average pooling, low, smooths out values. And global max pooling, well, it takes the max value, so it is high, but global average pooling is low. So here, sensitivity to outliers, if you have a use case that you don't want to be sensitive to outliers, you may use average pooling. But in other cases, when you don't have sensitivity with extreme values, with sensitivity with outliers, you can use average pooling. So as a machine learning engineer, you have to know which one you choose at the right time. Then, typical use case, emphasize sharp edges. So the max pooling emphasize sharp edges. As you can see here, we have max pooling layer. This max pool layer emphasizes the sharp edges. So we have here edges. As you can see, the edges here are emphasized, or these edges pixels are now activated. Okay, so we have in max pooling emphasizing sharp edges / key features, but average pool flatten minor variations, denoise. It denoises the features, flatten minor variations. Global max pooling, final layer before classification. Here we have an important question. Where or when do you use max pooling, average pooling, global max pooling, and also global average pooling? Well, these two, global max pooling, global average pooling, you will always use them before the classification head, before the classifier layer. So we have here a classifier layer, that classifies into different classes: lifeboat, pizza, pelbaba, and so on. So before the classifier layer, before the classification head, we have, after the max pool layer, here we have, if you click on this, we have a flatten layer. You could replace this flatten layer with average pooling, global average pooling, or with global max pooling. Okay, but the max pool layer or average pool layer are used within the network, within the layers, in between the layers. But when you want to classify into, when you want to condense the features into a vector, you may choose between the global max pooling or global average pooling. But max pooling, average pooling are used within the layers, are used within the feature extraction layers. Okay, as you can see, max pooling here are used and generates a feature map, a matrix. This matrix couldn't be used with fully connected layers. We have, in order to be able to process data or to input data into fully connected layers, you have to have a vector. So you must have a vector, because fully connected layers process 1D data. Global max pooling, global average pooling produces a vector, produce vectors, while max pooling, average pooling produces feature maps, produces matrix, two-dimensional data. Okay, we have height and we have width. So we have 2 dimensions. So it's important to know which one to use. Now we have here effect on training, max pooling, strong localization, may lose context. So there is a downside of max pooling. You may lose context. You may lose some important features, lose some important patterns. Average pooling keeps broad context, may blur fine details. So average pooling, if you use average pooling, it may blur the fine details because it takes the average trend. And global max pooling, strong signal but may overfit to spikes. Global average pooling, better generalization, smooth final signal. And you will see in many architectures they use this one, global average pooling, before passing the image to a fully connected layer. So here in GoogleNet we are using global average pooling to pass it to compact the features into a fully connected layer. Used in VGG, so max pooling is used in VGG, ResNet, layers. Average pooling, some classical CNN like LeNet hasn't used, or LeNet didn't use max pooling. LeNet used average pooling. So LeNet used average pooling as a subsampling technique. But VGG, keep in mind that VGG, ResNet, the early layers used max pooling. Global max pooling in lightweight models, for example MobileNet. As I said, MobileNet takes the MobileNet uses the global max pooling to capture the strongest activation from each channel. And we have global average pooling in Inception. Now we are studying Inception. So global average pooling is used in Inception, in ResNet, but before classification head. For classification head, the last layer, this fully connected layer, is called a classification head. The head that classifies into said amount of classes. And we have analogy, max pooling. Its analogy is, what is the brightest spot? So what's the brightest spot? Average pooling, what is the average light level? So what is the average light level? And global max pooling, where is the peak across the whole image? So the peak is the highest value, the biggest value, the largest value across the whole image. And we have global average pooling, how bright is the image overall? So we are taking the overall average. Featured paper, here we have the Inception GoogleNet paper 2014, Going Deeper. It's named as Going Deeper with Convolutions. The author is Christian Zijedi with Weilu and et al. We have here the introduced multi-scale processing, or they introduced multi-scale processing and bottleneck architecture. GoogleNet saw multiple realities at once. So GoogleNet didn't just use a single filter size, but rather uses multiple scale scenes or multi-scale perspectives at one glance in parallel simultaneously. So GoogleNet saw multiple realities at once, processing textures, shapes, and edges in parallel efficiently and with purpose. So sometimes when you want to understand a concept in mathematics or physics or chemistry, they say you have to look to this equation or this phenomena from different ways, or to look from different angles, or to look from different lens. Here they applied this smart technique. They used different filter sizes, different window sizes to learn the best features, whether it was one by one to learn very local details, fine-grained details, or 3x3 convolutions to learn mid-level features like textures and edges, to learn medium level features and patterns, and also 5x5 convolutions to learn larger context and larger components of the image. And Christian Sigidi is the author of this paper. So if you go here, they recently got a prize from Google Research. As you can see here, we have Google, the official account on X of Google Research. Okay, so here you can see congratulations to the authors of Going Deeper with Convolutions, which is the nice GoogleNet architecture recipient of the 2025 Langwit-Higgins Prize, which celebrates a paper released 10 years ago that has had a significant impact in the field of computer vision. And if you click on this, you can go to the paper of Going Deeper with Convolutions, and feel free to read here in your own time and explore more. Now we have finished discussing the important aspects about GoogleNet and Inception. As you can see here, the architecture, we have this architecture. They have Inception blocks and auxiliary classifiers, and also they used different kernel sizes to look at the image from different ways or from different perspectives. Now we have finished discussing GoogleNet. Let's move on to Highway Networks 2015. Now let's discuss Highway Networks 2015. Philosophy: trainable depth highways. By adding trainable gates to skip connections, so a very important concept, skip connections, highway networks learned when to skip or transform data. This blended the resilience of identity pathways with adaptive transformation, paving the way for easier optimization in very deep networks. And here, as you can see in the image, we have, if we clear this, as you can see in the image, highway networks architecture, you can see that we have two types implemented in the paper highway networks. We have two types or two variants. The first variant is fully connected layers. We have the fully connected version where we have an input, then we have a carry gate, transform gate, then we have fully connected layer, then we apply a transform gate, then a fully connected layer, followed by a transform gate, followed by fully connected, and then at the last we have softmax layer. And also we have another variant, we have another type of this architecture, highway networks, which is convolutional highway layers, where we have this architecture or this type of architecture. Input, then we pass the input to a carry gate. After the carry gate, we apply a transform gate. Then we have carry, transform gate. Then we pass it to a convolutional layer. You can see that we have now a convolutional layer. In the fully connected version, we have fully connected layers, but here we have convolutional layers. Then we have transform gate, convolutional layer. Then at the last or at the end, we have a softmax layer to classify. Highway networks configurations with fully connected FC and convolutional conv highway layers. And here we have this image also. You can see we have two blocks. The right hand side block which is the orange block. We have here input data, and we pass the input data to this block. This block applies a set of hidden layers, applies a set or a group of hidden layers. These hidden layers could be fully connected or could be convolutional layers, and they are called transformation path. So we have the transformation path here. Okay, then we have also another block, the left hand side block, which is the gating. The gating mechanism decides whether to transform or to bypass the data. So whether to apply a transformation or whether to bypass and pass the data through the network. And if you go down here, we have the philosophy in action, how highway networks proved their core idea. Unimpeded information flow, information highways. So this is the first important pillar. We have unimpeded information flow concept inspired by LSTM. LSTM is an algorithm or is an architecture commonly used in natural language processing, and it is considered a recurrent neural network, an RNN. It is short for long short-term memory. So the highway networks are inspired by LSTM. LSTM, highway networks introduced transform, T, and carry, which is C equals 1 minus T gates, to regulate how much input is transformed versus passed to unchanged across layers. So the concept inspired by LSTM, highway networks introduced transform and carry gates to regulate how much input is transformed versus how much input is passed unchanged across layers. Evidence: the original paper declares that the architecture allows unimpeded information flow across several layers on information highways, enabling training of hundreds of layers with simple SGD. So SGD is short for stochastic gradient descent, and it is considered an optimization algorithm that optimizes the parameters, the internal weights and biases to better represent the data. So enabling training of hundreds of layers with simple SGD. Philosophical significance: depth is preserved when identity flows are preserved. Layers become optional exits for transformation. So here we have this important concept or important aspect. Depth is preserved. So if you want to preserve depth, if you want to train very deep networks, really deep networks, that could be possible only when identity flows are preserved. Layers become optional exits. Transformation. The second pillar, we have adaptive depth, learning when to transform or bypass. So the highway networks learn when to transform and when to bypass. So it's a learned aspect, learning when to transform or bypass. Concept: gates learn to determine per input whether to apply nonlinearity or preserve information. When T is near zero, the layer acts as transparent. When T is near 1, it transforms. Evidence: highway networks use skip connections modulated by learned gating mechanisms. So the gating mechanisms here are learned. They are learned gating mechanisms. The advantage is its ability to overcome or partially prevent the vanishing gradient problem. So we have a common problem in deep learning known as the vanishing gradient problem, and they always try to mitigate this problem. They always hardly try to reduce this problem. Philosophical significance: the network dynamically controls how deep each input goes, creating paths of varying effective depth. So this is a really important concept. So the network, the highway network, the highway architecture dynamically controls how deep each input goes. So the depth is learned, the depth is learnable, creating paths of varying effective depth. So some inputs needs to go deeper than other inputs. Some inputs doesn't need to go that deep. Enabling extreme depth. This is the third pillar. Enabling extreme depth. Hundreds of layers. Okay? Concept built to be trainable. So the highway networks built to be trainable with SGD and various activations, demonstrating that extreme depth is possible. Extreme depth is possible in feed-forward networks. So as we said, built to be trainable with SGD and various activations, demonstrating that extreme depth is possible in feed-forward networks. Evidence: the authors wrote that highway networks with hundreds of layers, so they have a 900 layers. Okay, so they trained until 900 layers. So with hundreds of layers can be trained directly with SGD. Philosophical significance: depth becomes feasible. Now the depth is now feasible. Depth is possible with highway networks, not just theoretically valuable, but practically attainable with modular gate control. So we have the gate mechanism, the gating mechanism, which decides whether to transform the input or whether to bypass the input, whether to skip. Mitigating vanishing gradients with learnable gates. So this is the fourth pillar. This is an important aspect. As we said, vanishing gradients is a real problem in deep learning. Concept: the gating mechanism allows gradients to safely bypass deep nonlinear transformations, reducing vanishing gradient issues. Evidence: researchers noted highway layers addressed this limitation, enabling the training of networks even with hundreds of stacked layers. As we said, they trained up until 900 layers. So they had an experiment with 900 layers, which is really deep. If you think about it, most architectures don't have this number of layers. So this is considered a really deep architecture, very deep architecture. A magnificent architecture addressed this limitation, enabling the training of networks even with hundreds of stacked layers. Philosophical significance: depth is safe when you can selectively preserve gradients, preserve identity. A highway network gives the option to bypass the funneled path. Philosophical table: validation of trainable depth. So here we have philosophy pillars in highway networks. Philosophy pillar: identity plus gating equals highway. So the highway architecture is a combination of identity, the preservation of identity, preserving identity, an image of the truth image of the original image of the data, and also plus gating. As we said, the gating mechanism decides or determines whether to bypass and whether also to transform, apply the transformations. Transformations here, a transformation is a learned nonlinear function, which could be a densely connected layer, fully connected layer, or convolutional layer. Information highways enabled T and C gates. Adaptive layer utilization: gates trained to skip or transform per input. So the gates trained to skip, whether to skip or transform per input. And also hundreds of layers tractability, demonstrated training of 50 to 100 plus layer networks with SGD. Gradient preservation through depth: empirical claim of mitigation of vanishing gradients. We always try to reduce the vanishing gradients problem. Philosophical insight: highway networks envisioned deep neural networks not as monolithic pipelines, but as dynamic controlled highways, where each layer decides whether to transform or carry forward information. So whether to carry forward information, whether to bypass information in a feed forward fashion, or whether to transform and apply a land nonlinear function on the input. This modular input aware gating mechanism gave depth the freedom to scale. So highway networks gives neural networks the freedom to scale by its own adaptability. So it trains the neural network to be as freedom as it needs. The input can go deeper as the input needs to go deep. And who determines this? The depth, the gating mechanism. The gating mechanisms determine whether we should pass the input further or whether to transform. So this modular input aware gating mechanism gave depth the freedom to scale, shaped the structure of modern skip connections. So they shaped the structure of modern skip connections and set the stage for ResNet's simpler yet powerful identity-based highways. Featured paper, here we have the paper Highway Networks 2015 training, and the paper is titled as Training Very Deep Networks, a critical step toward ResNet's identity mapping revolution. So we have here and the author of this paper is Ramesh Kumar and et al. So they invented the architecture of highway networks, and here we can read this. Highway networks reimagined depth as a dynamic route, not as a tunnel. So highway networks reimagined depth as a dynamic route. So the depth now is dynamic. The depth is learned. The depth is trained. The depth is not anymore rigid. So highway networks reimagine depth as a dynamic route, not as a tunnel, with adaptive gates deciding which layers transform and which simply pass. And we can check the view inline paper. So view inline, you can read through this paper in your own free time, so feel free to learn about it. Here we have highway networks. This is the paper by Ramesh Kumar and the rest of the authors. Abstract, there is plenty of theoretical and empirical evidence that depth of neural networks is a crucial ingredient for their success. However, so here we have inferred an important lesson that the depth of neural networks is a crucial ingredient for their success. However, network training becomes more difficult with increasing depth. So always keep in mind that the more deeper you go, the more challenges you will face, like the challenge of overfitting, the challenge of vanishing gradients. Okay, so you need to tackle these challenges. You need to deal with these challenges. Here they said, however, network training becomes more difficult with increasing depth, and training of very deep networks remains an open problem. In this extended abstract, we introduce a new architecture designed to ease gradient-based training. So they tried to make the process of gradient-based training easier of very deep networks. We refer to networks with this architecture as highway networks, since they allow an embedded information flow across several layers on information highways. The architecture is characterized by the use of gating units. So the architecture is characterized by the use of gating units. So they have units of gating mechanisms which learn to regulate the flow of information. So this is an important concept, the flow of information through the deep neural network. Through a network, highway networks with hundreds of layers can be trained directly using stochastic gradient descent SGD, and with a variety of activation functions, opening up the possibility of studying extremely deep and efficient architectures. So feel free to read through that architecture. You can explore the equations here. You can see we have if t equals 0, then return I, ft equals 1, then return this function h. And you can, here we have, we use a boldface letters for vectors and matrices, and italicized capital letters to denote transformation functions. 0 and 1 denote vectors of zeros and ones respectively. And here you can say, and here you can see that constructing highway networks, convolutional highway layers are constructed similar to fully connected layers. So they have, as we said, they have two variants. They have two types of the architecture. Convolutional highways layers are constructed similar to fully connected layers. Weight sharing and local receptive fields are utilized for both H and T transforms. We use zero padding to ensure that the block, state, and transform gate feature maps are the same size as input. And here you can see training deep highway networks for plain deep networks. Training with SGD, stochastic gradient descent, stalls at the beginning unless a specific weight initialization scheme is used, such that the variance of the signals during the forward and backward propagation is preserved initially. So they use GoogLeNet initialization. This initialization depends on the exact functional exact functional form of H. And you can go down here. You can see here we have this equation, which is x multiplied by the weights plus the bias. This is a linear function, and W is the weight matrix. So W transposed. So why do we have to transpose? This is a important concept. When you multiply a matrix X, X represents the inputs to the layer. We have to transpose the second matrix. In order to perform matrix multiplication, we have a rule in linear algebra. We have a famous rule in linear algebra. We need to transpose the weights matrix. So here W is the weight matrix, the matrix that holds the weights, and B the bias vector. So notice the weights are stored in a matrix. You will commonly hear the weight matrix, but the bias is called the bias vector for the transform gates. And here you can go. Yep, we have here optimization. So experiments. Very deep plane networks become difficult to optimize. So here you can see that there is an issue in the plane networks. Very deep plane networks become difficult to optimize, even if using the variance preserving initialization scheme from He initialization. To show that highway networks don't suffer from depth, in the same way we run a series of experiments on the MNIST digit classification dataset. We measure the cross entropy error on the training set to investigate optimization without conflating them with generalization issues. And also, if you go down here, so here you can see that the number of parameters you can read about it. We were also able to train thinner and deeper networks, a 19-layer highway network with 1.4 million parameters, and a 32-layer highway network with 1.25 million parameters. Both perform similar to the teacher network of Romero. Okay, and also you can see here we have the highway networks. These plots show us the x-axis number of epochs, and here the mean cross entropy error. So the y-axis represents the mean cross entropy error. You can see the error or the loss function goes down, so the loss curve goes down when and the x-axis represents number of epochs. Okay, and here we have a table of number of layers, number of parameters, and you can read through that. Accuracy. So as we said, number of layers, number of parameters determines the size of the model, and accuracy determines how performant the model is. So here we have conclusion. Let's read the conclusion. Learning to route information through neural networks has helped to scale up their application to challenging problems by improving credit assignment and making training easier. Even so, training very deep networks has remained difficult, especially without considerably increasing total network size. Highway networks are novel neural network architectures which enable the training of extremely deep networks using simple SGD, while the traditional plain neural architectures become increasingly difficult to train with increasing network depth, even with variance preserving initialization. Our experiments show that optimization of highway networks is not hampered even as network depth increases to 100 layers. So even if you train a highway network with 900 layers, it will converge faster, and also it will not suffer from the vanishing gradients problem. Why? Because they introduced the skip connections or the preserving identity preservation to allow the model to learn useful features. So now we have finished discussing the highway networks. In this section, we will discuss pathways of preservation, a philosophical bridge across deep learning. Pathways of preservation makes the flow of information stable and the gradients stabilized across the whole architecture. The farther back you can look, the farther forward you are likely to see. Winston Churchill. The farther back you can look, the farther forward you are likely to see. So when you remember the past, you can farther forward you are likely to see. The farther forward you are likely to learn. Deep learning models, like minds, don't merely compute, they structure, carry, and refine representations of information across layers. In the evolution of deep architectures, one key idea has quietly emerged as central: preserving information signals rather than discarding or over-transforming them is critical for depth to be meaningful. So deep learning models, like minds, needs to be refreshed, needs to be reminded. So you have to remind the later layers, the deeper layers, what the original X looked like. Don't merely compute. So these layers don't merely compute, but instead they structure, carry, and refine representations of information across layers. In the evolution of deep architectures, one key idea has quietly emerged as central, as significant: preserving information signals, making them powerful across the architecture. If you keep the signal powerful across the whole architecture, across layers, across the whole depth of the architecture, rather than discarding or over-transforming them. So you don't need to over-transform the X. You don't need to discard important signals, to discard important gradients. So rather than discarding or over-transforming them, this is a critical for depth to be meaningful, and also to enable the idea of going deeper and deeper. To be able to go deeper and deeper, you have to preserve signals. You have to protect the signals from getting weaker and weaker, because the more deeper you go, the more chance these signals will get weaker and weaker and weaker until they die. To make the signals alive and to keep the momentum going strong and strong, then you need to preserve the identity. You need to pass or use skip connections to preserve the original X. Skip connections. A hidden philosophy across architectures. From early convolutional networks to modern transformers, the path of progress has consistently favored models that can retain essential features, whether spatial, temporal, or semantic, through depth. This isn't memory in the literal neural sense, but architectural design that protects and reuses valuable representations. So from the early convolutional networks to modern transformers, these all architectures needs to be reminded, needs to have some sort of memory to be as stable as wanted, the path or as desired. The path of progress has consistently favored models that can retain, protect essential features. So if you have an architecture that retains essential and significant features, then this is a powerful architecture, because you are keeping the momentum of strong features. The information flow, preserving the information flow, whether spatial, temporal, whether it was spatial in images, temporal in time series, or semantic in some data points, through depth. This isn't memory in the literal neural sense, but architectural design. It's kind of an architectural design that protects or that preserves and reuses valuable representations. LeNet 1998, structured representation, philosophy, from pixels to patterns. So moving from pixels to patterns. LeNet was one of the first CNN's architectures, and it introduced the idea of convolutional layers. LeNet demonstrated that hierarchical feature extraction through convolution and pooling can preserve spatial coherence, guiding the network from raw input to meaningful abstraction. So through this pattern of convolution and pooling that was introduced by LeNet 1998, LeNet was able to preserve spatial coherence, to preserve or protect the spatial features, guiding the network from raw input to meaningful abstraction, to meaningful representations. AlexNet 2012, scaling with structure. So now they scaled up the depth, they deepened the network, but with structure. AlexNet deepened this structure dramatically, leveraging GPUs, graphical processing units, to accelerate computations, ReLU for faster convergence, rectified linear unit activation functions, and drop out, the king of regularizers, to reduce the risk of overfitting, to go deeper and deeper. So they enabled the idea of going deeper and deeper. But its convolutional layers still maintained locality and spatial consistency, critical to avoiding loss of essential visual patterns during learning. So here we have a downside of AlexNet, which is its convolutional layers still maintained locality and spatial consistency, critical to avoiding loss of essential visual patterns during learning. Then we have this idea of VGG, or the architecture of VGG, uniform depth with predictability. So uniformity and simplicity with predictability. VGG built very deep networks using uniform 3x3 convolutions, showing that consistent architectural rules could sustain effective feature composition layer after layer, creating predictable and stable representational flow. So VGG built a consistent architecture, a uniformed architecture, very deep networks using uniform 3x3 convolutions, showing that consistent architectural rules could sustain effective feature composition layer after layer, creating predictable and stable representation flow or information flow across the architecture. Inception 2014, GoogLeNet. It's called Inception or GoogLeNet, multi-scale perception. Inception introduced parallel filters of various sizes. So they introduced the idea of parallel filters, 1x1 filter, 3x3 filter, 5x5 filter. Each filter sees the image from a different angle. Each filter sees the image from a different way, allowing each layer to process information at different resolutions simultaneously at the same time. Rather than choosing one filter size, it captured context from multiple receptive fields, enhancing representational richness. So in the enhanced representational richness. Then we have highway networks. Highway networks 2015, gated information, gated transformation. A shift occurred. Now we have a new paradigm in deep learning. A shift occurred. The architecture learned to decide whether to transform or carry forward a feature. Carry gates allowed signals to bypass transformation, creating pathways that preserve unmodified representations, key to enabling much deeper models. So here we have the idea of the architecture learned to decide whether to transform the X more and more and more, or whether to bypass the X, skipping those transformations. So this idea of deciding whether to transform or carry forward a feature was a new landmark shift in deep learning. Carry gates allowed signals to bypass transformation, creating pathways, creating skip connections that protect unmodified representations. So sometimes we don't need to transform the X using every single operation, using every single layer. Sometimes we just need to bypass it, to just keep it as it is. Why? Because when you keep the X as it is, you make the later layers remember or remind itself what the original X looked like, what is the shape of the original X. So here, that preserve unmodified representations, key to enabling much deeper models. Then we have ResNet, Residual Nets, 2015, preserving identity. ResNet distilled this principle into a simpler yet powerful mechanism: residual connections, residual skips, by adding the input directly to the output of a block. So by adding here, okay, the input directly to the output of a block, the model learns what to change. The model learns what is remaining to learn while preserving what works. This allows depth without degradation. Okay, so ResNet distilled this principle, refined this principle into a simpler yet powerful mechanism: residual connections, by adding the input directly to the output. So every single block produces an output, and then we add to this output the input that was inputted to this block. This idea of combining the output plus the input makes the architecture, or allow the architecture, to go deeper and deeper without forgetting what it learned, without getting stuck in what it was learning. In fact, the model learns what to change. The model focused on the change, not learning everything. The change, the learned features minus the real input. So we have the f of x, the transformed version of x, which is the feature maps, minus x. This idea is the idea of residual connections. Then we have transformers, 2017 plus, contextual preservation at scale. Transformers introduced self-attention, enabling each token or patch to contextualize itself relative to all others. Combined with residuals and normalization, this architecture ensures that early representations remain accessible and modifiable, supporting both local and global understanding. So transformers also utilized the idea of residual connections by passing the inputs directly to the outputs, and also to make the deeper layers, the deeper architectures, the deeper components remind its mind, refreshed its minds with what the data point X is. Transformers introduced self-attention, which is a mechanism that attend or focus on the most important features, enabling each token or patch in images. So if you are dealing with text, you divide the text into tokens, you separate the text into tokens or the image into patches to contextualize itself, to build a context relative to all others, combined with residuals and normalization. This architecture ensures that early representations remain accessible and modifiable. Then we have LSTM and GRU. LSTM is an algorithm short for long short-term memory, LSTM, and GRU, gated recurrent unit, temporal representation control. In recurrent models, in recurrent neural networks, depth exists in time. Depth lies in time. LSTM and GRU introduced gating mechanisms that let models retain, forget, or expose temporal information selectively. This is true state preservation, optimized for understanding sequences with long-term dependencies. So when you have long-term dependencies, when you have long context texts, then you may want to use algorithms like LSTM that preserves an internal memory, an internal loop or memory to remind itself with the previous tokens. So LSTM and GRU introduced gating mechanisms that let models retain, forget, or expose temporal information selectively. This is true state preservation. Unifying and site preservation enables generalization. So we have an important rule in deep learning: preservation enables generalization. When you preserve the real identity, when you preserve X, preserve the flow of the information, then you are enabling generalizable models. You are building generalizable models across modalities, whether it was vision, language, or audio. The most effective deep models are those that preserve useful signals, preserve strong and active signals throughout the architecture. Learn what to change, not just learning new patterns, but also learning the change and what to carry. Retain relevant context across space and time. This is not memory in the LSTM sense, nor in the colloquial sense. It is information preservation. It is features preservation, keeping the gradients stabilized and stable by design, a structural and architectural commitment to not to forget what matters. So just like human minds, you then and sometimes needs to refresh your mind with some concepts, with some, for example, if you are studying math and you after 1 month studied, for example, some equations or some principles, you need to refresh your mind with those principles. Also the network across time or across depth, whether you are dealing with NLP, then you are moving across whole long texts. Along long texts you need to keep context. Or you are dealing with CNNs maybe doesn't have that much long dependencies, but have deep models, depth in the depth. After a while the model will forget what it learned. Then you need to refresh the mind of the layers with what it was learning. So here, this is not memory in the LSTM sense, nor in the colloquial sense. It is information preservation, information protection by design, a structural and architectural commitment to not to forget what matters and to build robust models. A bridge to the future. From LeNet to transformers, the history of deep learning is not only one of scale, but of philosophical maturity. Transformation must be tempered by preservation. Depth must be anchored by identity and structure. Prediction emerges from continuity, not fragmentation. In this light, architecture isn't just code, it is cognitive engineering. So now we have finished discussing the idea of pathways or the skip connections, residual connections. We will move on to ResNet architecture in the next section. Now let's dive into one exciting architecture, which is ResNet. ResNet is short for residual network or residual neural network. Its philosophy is focus on change, preserve identity. So the main philosophy behind ResNet is to focus on change, to focus on the difference and preserve identity. ResNet revolutionized depth. So if you zoom in, ResNet revolutionized depth by having layers learn only the residual changes to identity mapping. Skip connections ensured signal flow and enabled training of truly deep models, shifting the deep learning paradigm fundamentally. So as we said, ResNet, residual neural network, revolutionized depth by having layers. So we have layers learn only the residual or changes, the difference to identity mapping. We have this new type of component which is called skip connections. Skip connections ensured signal flow. So it stabilizes the flow of the signals and enabled training of truly deep models. And by the way, if you don't know what a signal is the gradient error. So it stabilized the signal flow across the whole neural network architecture from the start, from the very first layer to the very last layer, and enabled training of truly deep models. So before, deeper models was worse, or deeper models were worse than shallower models. Shallower models were better than deeper models, and this happened because the gradients were vanishing. So we had the problem of vanishing gradients. The gradients vanished by reaching the very last layers. The gradients are very small, near zero. So the signal is low. The signal is not informative. It doesn't tell the neural network that much information to update the weights, to update and modify the weights. And we always need useful, helpful signals to inform the neural network when to modify, whether to increase the weights, to decrease the weights. So we want to keep the signal strong. We want to activate the signals. We need to make the neural network alive through the whole architecture. So they enabled the training of truly deep models, shifting the deep learning paradigm fundamentally. And as you can see in this nice image, we have three architectures. We have VGG 19. So you can see we have here VGG 19 model, and we have this architecture. You can see VGG 19 doesn't have any residual connections. We don't have any connections or residual connections, skip connections between the layers. Then we have 34 layer plane. So this is a plane neural network consisting of 34 layers. So we have here 34 layers but without skip connections. And here we have a 34 layer residual. So now we have these residual connections. We have these skip connections that passes the identity or passes the original data between layers. Why? To make the later layers here remember the original look of the image, to remember the original shape of the image, and also to remember the features and patterns as in the truth image, to preserve the flow of information, and also to preserve the gradient flow across the whole architecture. So as you can see, we have here convolutional layers. So we have conv by and you can see that all of these convolutional layers have 3 by 3 kernel size. So here you can see we have 3 by 3 kernel size, 3 by 3, 3 by 3, 3 by 3. So consistent kernel size across layers. And then we have average pool. As we said, the average pool layer averages every single channel into a number, into one number. So we have 3 channels, red, green, blue, and it averages them all into one number. It takes the average, the overall trend, and passes it to a fully connected layer that classifies into 1000 neurons as an ImageNet dataset. Now, as you can see in the image, ResNet block architecture, we have this ResNet block architecture. You can see we have the X. X is the identity, is the truth image, the truth data point. And here we are passing it. We have here a skip connection. We have a connection that passes it through here. And here we have X passed to a layer. This layer does some mathematical operation on the X, and then it passes it to another layer. This layer also does a mathematical operation, does some operation on the image. Layers in deep learning always manipulate the X, manipulate the data point, and then it outputs some output, and we combine the X, which is the truth image, the unprocessed input data, with the processed feature map. So we combine these both, and it gives us a useful features, give us more strong activations with powerful signals to inform the architecture when to update weights. So you can see here we have identity mapping. Now let's talk about the philosophy in action, ResNet's core validation. Residual learning easier than learning identity. So we have residual learning. learning the difference, learning the change. Because when you pass, for example, imagine you are training a network on images of elephants. So when you pass an image of an elephant, this image goes through the architecture. When it goes through the architecture, through the layers, these layers extract features. They do feature extraction. And if you go deeper and deeper, then this image might be, let's say, doesn't represent the truth image anymore. So when you remember the architecture by the truth image, when you make a reference to the truth image, then the architecture will be able to represent the data better. Will be able to detect the most appropriate weights. It will have an equal opportunity to learn the features. So when you pass, for example, as we said, an image of an elephant through layers, the very first layers will have an opportunity to learn the truth features as they are more than the later layers. Why? Because the later layers will only see the outputs of those layers without seeing the truth image as it is. But when you do some skip connections, when you remember these layers, what the look of an elephant in real way, what is the look of a real elephant, when you do a skip connection and always show the later layers what an elephant looks like, plus combining with the features learned from these layers, it will have more stabilized feature learning. And also, it will preserve the flow of information to be stabilized. And also have an equal chance of learning. An equal chance. So here you can see concepts. Instead of learning a full mapping, h of x, so instead of learning a full mapping, which is h of x, ResNet learns only the residual. Learns only the residual, the difference, the change, the residual. F of x equals hx minus x. As we said, x represents the truth data point. Data point, whether it was image, voice, audio, whichever data you are dealing with. X represents one sample. And h of x is the function h applied to the x. So here x is the same as this, but we applied a transformation. Whether it was convolution, dense layer, whatever mathematical operation you are doing or applying on the x. So when you subtract h of x from x, then you are taking the residual, the difference, the change between what are the learned features minus the whole image. The network's block computes this transformation. Reasoning. Learning a function that maps close to 0 is easier than forcing a deep stack to replicate the identity function. If the optimal mapping is identity, ResNet achieves this effortlessly by driving f of x towards 0. So here we have an important concept. Reasoning. Learning a function that maps close to 0, so we always want to make the difference between the truth image and the learned features 0, go near 0, go towards 0. So learning a function that maps close to 0 is easier than forcing a deep stack to replicate the identity function. So instead of creating a deep stack that replicates an identity function, we want to learn a function that maps close to 0. If the optimal mapping is identity, ResNet achieves this effortlessly by driving f of x towards 0. The second pillar, so here the first pillar is residual learning, change learning. As we said, the core philosophy about ResNet is that focus on change. We are focusing on the change, on what the feature, what the image looks like, and what was learned. We are comparing what this layer has learned plus what are the features in the real image, and taking the change. Preserve identity. Why? To preserve identity, an important paradigm in modern deep learning. As we said, residual learning easier than learning identity. Then the second pillar is uninterrupted signal flow through identity shortcuts. So by the way, another name for skip connections, we can call it shortcuts. Shortcut connections. Forward path. Signals can traverse through many layers via identity connections, effectively bypassing convolutions when unnecessary, ensuring stable propagation all the way through the network. So here our goal is to stabilize propagation, to make the optimization process stable. So all the idea is that how can you make the optimization process stable? Why? Because the algorithm backpropagation, which is responsible for calculating the gradients based on the loss function and the weights, produces gradients. And by reaching the end of the architecture, these gradients will not become such informative, will not be informative, will be smaller, vanishing gradients. These gradients become smaller and smaller and have low signals. So thus, we want to ensure stable propagation, stable optimization, strong optimization across the whole architecture so that every single layer has an equal chance to learn. So the signals will die, will be dead, okay? So we want to ensure stable propagation, alive propagation, active propagation, all the way through the network. All the network layers have the same opportunity, the same chance to learn. Not the very first layers just learn and then the rest of the layers will be died, okay? So before, as we said, shallower models outperformed deeper models. And you will say, what? How do shallow models outperform deeper models? Well, because of the problem of vanishing gradients. Vanishing gradients was an issue in deeper models that prevented the later layers, prevented the upcoming layers from learning as informative signals as the very first layers. And why this happened? Because we don't preserve identity. We didn't preserve any of the original data. We have to recall the later layers to make the later layers remember what the original sample looks like. Okay? Backward path. Gradients can flow directly from deeper layers to early ones, reducing the risk of vanishing gradients even if individual layers have small residual contributions. And the third pillar is important: overcoming degradation in deep networks. Problem: plain deep networks like VGG 34 exhibit degradation, where adding more layers increases training error despite theoretical capacity. So VGG 34 exhibit degradation, where adding more layers, when you go deeper and deeper and deeper, add more and more and more layers, increases training error. Why? Because we don't preserve the identity, don't preserve the original shape of the data. So when you recall the later layers by the original look, by the original shape of the image of the data, then you are decreasing the degradation of the network. So here, as we said, we're adding more layers increases training error despite theoretical capacity. ResNet's solution: identity shortcuts ensure deeper networks can fall back to performance equivalent to shallower ones. The original 152 layer ResNet achieved 3.5% top 5 error on ImageNet, beating shallower baselines. So they solved the problem of vanishing gradients using identity shortcuts. Identity shortcuts preserved the look of the data, preserved the original or the truth features of the data. Then we have a fourth pillar: empirical validation. So thanks to connections, thanks to skip connections or residual connections, which preserve the identity, preserve the real features of the data. Now we have a fourth pillar: empirical validation, depth that actually works. ResNet variants like 50, 101, 152. So if you go to Torch Vision, by the way, and then go to Torch Vision is a domain library. So if you go to docs and then choose PyTorch domains, we have many different domains. So we want Torch Vision, okay? Here we have models and pre-trained weights. If you scroll down, you will find a long list of models, okay? So scroll down here. We have models like AlexNet, ConvNext, and by the way, all of the models, and we have here ResNet. If you go to ResNet here, well, we have the ResNet model is based on this paper, Deep Residual Learning for Image Recognition paper. And if you go down here, we have these variations. So we have ResNet 18, we have ResNet 34, ResNet 50, ResNet 101, ResNet 152. So ResNet is a family of models, is a group of models, is a collection of models, and these are the variants. So we have ResNet 50, 101, and we have ResNet 152. Okay, so the variants with 50, 101, 152, the same as here. We have 50, 101, 152. All improved performance without degradation, whereas plain counterparts failed. The follow-up identity mappings version, which is ResNet version 2, enabled 1001 layer models to be trained on Cypher, validating that pure identity shortcuts and pre-activation improve deeper architectures. So they enabled the idea of going deeper. ResNet started a new era of building deep, really deep neural networks architectures. Because there's a downside of going deeper, which is if you go deeper and deeper and deeper, there's a chance that the later layers will forget what you learned, will forget what the original X look like. But if you preserve the identity, you always make the network refreshes its mind, refreshes its memory with what the real X looks like. Okay, so you need always to refresh the network's memory with what the X looks like, what the real X looks like. The core role of connections in deep learning. In the depths of learning, only what flows survives. So here we have an important saying. In the depths of learning, so when you go deeper and deeper and deeper, this is the world of deep learning, only what flows survive. So what gets outputted from the layers, just this survive. So the outputs, the feature maps that gets outputted by the layers, so we have convolution layer, max pooling, convolution, what gets outputted of the features, these only will survive. The rest will be discarded. And this is a problem, will cause the problem of vanishing gradients. But if you make the layers remember what the real X looked like, then you are making the architecture always refreshes its mind what the real X looked like. So only what flows survives. Across deep architectures, from highway networks to ResNets to transformers, one role has remained scared. Connections must preserve and facilitate information flow. So connections, the skip connections must preserve, keeps, protect, and facilitate information flow. So we must protect the information flow across the architecture. Highway networks introduced gated connections. So the type of connections, the kind of connections used in highway networks was gated connections. Gated connections. And as we said, the gating mechanism decides whether to transform the X and whether to pass it through unchanged. So we can pass X through unchanged, or we can transform X more and more. So introduce gated connections, giving the model a choice to either transform or carry information intact. ResNet embraced identity shortcuts, while ResNet embraced the idea of identity shortcuts, ensuring that signals could bypass transformation entirely when needed. Transformers employed residual attention pathways, enabling every token to retain its original identity while attending globally. And why do all these forms persist? Because their essence is the same: to bridge layers is optimization. So to bridge the problem of going deeper, to bridge the layers is optimization, to make the optimization process easier and more stable, preserve semantics, to preserve the semantic meaning of the features, the semantic patterns, and not to forget what the real image looked like, and support gradient propagation. Then we have a philosophical essence of preserve signals. So why do all these forms persist? Because their essence is the same to bridge layers, ease optimization, preserve semantics, and support gradient propagation. Philosophical essence: preserve signals from early layers, avoiding information decay. So we want to avoid information decay. Also facilitate gradients during backpropagation, combating vanishing effects. Enable depth without degradation in performance. So we enable depth without degradation in performance. Support abstraction while maintaining memory and identity. Regardless of their mechanism, whether it was gates, so the gating mechanism in highway networks, identity in ResNets, identity shortcuts, or attention in transformers, these skip connections are not engineering tricks. They are the philosophical threads that keep intelligence alive as architectures deepen. So you want to keep the intelligence alive and have the same momentum across the whole architecture without any degradation in performance as the architecture go deeper and deeper and deeper as architectures deepen. Essence of connections across architectures. Architecture, we have highway networks. Well, highway networks type of connection, gated skip connections. So we have gated skip connections, or the gating mechanism inspired by LSTM, long short-term memory. Transform gates plus carry gates. Control the flow of information, so they made the flow of information stable and optimized. Control the flow of information across layers via learnable gates, and these gates were learnable. Learnable meaning dynamically adjusting itself. So they trained a net of 900 layers, and the network decides how much this input should go deep. How much deeper should we pass this input to? Okay, so the architecture decides by itself via learnable gates, deciding how much to transform input versus how much to pass through unchanged. Enables deep models to learn selectively and maintain signal strength. So always we want this signal strength to be maintained, to be preserved, to be kept and not dead. We don't want to make the strength of the signal go lower and lower or decreased, or to be like dead signal. We want to keep it alive, strong, activated, to tell the network when to update the weights. The signal is the gradient era. The signal learning is called the gradient era. Backpropagation will compute the gradients, and then these gradients will tell us based on the loss function how much error we have, and based on this error the gradient descent algorithm will update the weights and update the patterns, the internal configurations. So here, as we said, the type of connection is gated skip connections, while in ResNet we don't have the gating mechanism. We now have identity skip connections. So you have to differentiate between the mechanism of connections. The type of connections in highway networks was gated skip connections, whereas in ResNet we have identity skip connections, residual addition, y equals f of x plus x. And as you can see here, y is the output equals f of x, so the transformed version of x, the version of x that is applied convolution on it, plus the real ground truth form of x. Preserve input information by directly adding it to the transformed output. So we are adding the input information by directly adding it to the transformed version, f of x. This bypass, we also call it bypass, prevents degradation in deep models and ensures gradient signals can propagate easily. So we always, our goal is to make the gradient signals to propagate easily and in a strong way. Transformer. Residual connections plus multi-head attention. So we have multi-head attention. Here we have residuals, maintain and combine original inputs with transformation. And we have attention, dynamically connect all positions in the sequence to allow contextual information exchange across distant tokens. So you can notice that we have three important architectures, three important types of neural networks, they all applied the idea of skipping connections, residual connections, or bypassing the identity, keeping the truth data always in the mind of the net to remember itself what the real X looks like, and then it learns the change. It learns the difference between the X and the transformed version of X. Across architectures, the essence is the same. Connections exist to carry memory. So we have a mechanism of carrying memory across the whole architectures, across the whole layers of the network. Enable learning. So we enabled the learning, the deep learning era, and preserve identity throughout deep representations. Philosophical summary. We have here pillars and how ResNet validated it. Preserve identity. So as we said, identity is the X. Okay, so we are preserving the identity. How ResNet validated it? Residual blocks can reduce to identity easily. So f of x equals 0. So our goal is to reduce the change, reduce the difference between f of x and also between x. So if you go f of x minus the sample x, it will give us equals y. So here we have this f of x equals 0. And then train change only. Learning residuals is easier than unknown transforms. So instead of learning unknown transformations, we are learning residuals. Difference change. Ensure stable signal paths. Forward/backward propagation via identity skips. So via identity skips, we are doing a forward and backward propagation, making the propagation optimization process stronger and activated. Always make the propagation system active throughout the whole architecture, and the momentum of the optimization process go stronger and active across the whole layers. Enable extreme depth. So we enabled 152 layer and 1001 layer networks with low error. So this was a game changer in the world of deep learning. Philosophical insight. ResNet crystallized depth as a strength, not a burden. By waving in identity highways, it reframed deep networks as iterative refiners. So we have a mechanism of iterative refiners to refine the gradients and to refine the patterns of the layers. Learning nuances instead of entire transformations. This philosophical pivot reshaped deep learning's trajectory, proving that focusing on change. So the philosophy of ResNet, remember, what is the philosophy? Is focus on change, preserve identity. We have to focus on change and also preserve identity to make the optimization process, the propagation process more stable. And as we said here, this philosophical pivot reshaped deep learning's trajectory, proving that focusing on change, difference, while preserving essence leads to powerful, scalable, and trainable models. And the author of the famous paper, Deep Residual Networks or Deep Residual Learning for Image Recognition, the author is Kai-Ming He and et al. So, revolutionized CNN depth by learning residual functions. And here we have the image of the author, Kai-Ming He. Instead of learning full transformations, ResNet learns the difference, and in doing so, made very deep networks feasible, stable, and superior. And you can read more about this architecture in the paper here, view inline. You can see that we have deep residual learning for image recognition, and if you go here, you can read the abstract. So here, the abstract is really important. Deeper neural networks are more difficult to train. So now they addressed the problem. They said deeper neural networks are more difficult, not easy to train. So we present, they said, we present a residual learning framework. So they introduced a new framework, a new paradigm, a new architecture in the world of deep learning. They presented a residual learning framework to ease the training of networks. So to make the training easier and more stabilized, as we said, they made the optimization process, the propagation process easier and stronger, and they also preserved the strength of the signals. So here, to ease the training of networks that are substantially deeper than those used previously, we explicitly reformulate the layers as learning residual functions. So the layers now are learning residual functions with reference to the layer inputs, instead of learning unreferenced functions. So before we had architectures like AlexNet, LeNet, AlexNet, VGG, Inception, GoogLeNet, they all learned unreferenced functions. Every single convolution passes its feature map, what it's seen, to the next layer. So this convolution layer, for example, seeing this feature map, then it produces the feature map and pass it to the next convolution layer. But the convolution layer, the next conv layer, doesn't see the image as it is. So now we pass a reference function. We do some reference skip connection to also show this layer, display to this layer what the original X looks like, to have an equal opportunity, to have an equal chance of learning the features, and also to focus on the change, to learn the change and difference. Okay, so here they said we explicitly, now this architecture reformatted the layers explicitly. So they explicitly used the technique of skip connections, reformulate the layers as learning residual functions with reference to the layer inputs, instead of learning unreferenced functions. We provide comprehensive empirical evidence showing that these residual networks are easier to optimize and can gain accuracy. So they have gains, new gains in accuracy, and can gain accuracy from considerably increased depth. On the ImageNet dataset, we evaluate residual nets with a depth to up to, as we said, 152 layers, 8x deeper than VGG. So note, they had an 8x deeper than VGG nets, but still having lower complexity. An ensemble of these residual nets achieved 3.57% error on the ImageNet test set. This result won the first place on the ImageNet Large-Scale Visual Recognition Challenge 2015 classification task. We also present analysis on Cypher 10 with 100 and 1000 layers, and also they trained an architecture of 1001 layer. Okay, and you can go deeper, and you can see we have this image. This image is residual learning, a building block. So this is a building block, the building block of the residual learning block. As you can see, we have X. X is the preserved identity, and we pass it to the output of the layer. We have here a weight layer, then we have ReLU layer, then we have weight layer. Weight layer is a kind of layer that have weights, and then we combine the X with the output to make the architecture learn what the previous layer seen plus what the real X looks like, and then we have this f of X plus X. And you can you feel free to read in your own time, so you can read here. Okay, and here they said shortcut connections. Okay, so practices and theories that lead to shortcut connections, and you can keep scrolling and read through here. And as you can see here, we have Cypher 10, and they also validated that on the ImageNet. If you go up, you will see that they tested ResNet architecture on ImageNet. So here they said training on ImageNet. So now we finished discussing the ResNet architecture, and here lastly we have the same image here. They have a VGG 19 architecture versus 34 layer plain versus 34 layer residual. Okay, so now we finished discussing the architecture of ResNet. We will move on to the architecture of wide ResNet, which is an optimized architecture upon ResNet. Now let's dive into wide ResNet, wide residual network, pre-activation ResNet. It is also called pre-activation residual network, ResNet, 2016-2017. Its philosophy is depth is not alone. Widen, reorder, parallelize. So now we have three important aspects. Width, so the width of the neural network, reorder, reorganizing the operations of the neural network, and also parallelizing the operations. Variants like wide ResNet, wide residual network, proved that width can replace depth. Pre-activation ResNet reordered operations to improve gradient flow, and ResNext added cardinality, parallel paths, each enriching ResNet's core concept for specific strengths. So, as we said, we have variants like wide ResNet. Wide ResNet proved that width, so we have width, the width of the network can replace depth. So here we have a new paradigm in deep learning. Width could replace depth. Pre-activation ResNet reorganized operations to improve gradient flow, to improve gradient stability, and ResNext added cardinality, parallel paths, each enriching ResNet's core concept for specific strengths. And as you can see in the image, we have wide ResNet block architecture. Here we have a basic block, convolution 3x3 kernel size, and we have convolution 3x3. Then we have B, bottleneck. The bottleneck, as we said, is a technique used in deep learning models, also used, if you remember, if you recall, in GoogLeNet, InceptionNet, to reduce the amount of parameters. It's a kind of regularization technique to regularize the amount of parameters. Then we have basic wide. So we have C, basic wide, as you can see, convolution 3x3 and convolution 3x3. Then we have wide dropout. Here you can see we have another image, okay, of wide ResNet block architecture. So as we said here, pre-activation ResNet. So we have now pre-activation. Wide ResNet block reordered the operations, rearranged the operations as like you can see. We have here a layer, weight layer, which is convolution layer, followed by BN layer, which is batch normalization layer. Then we have ReLU layer. ReLU is a activation function, an activation layer that enables the network to learn complex nonlinear correlations. And then we have another weight layer, which is a convolution layer. Then we have another batch normalization layer. Whereas in wide ResNet, in wide residual network, we have a new arrangement. We have a new organization of the layers, where we have the batch normalization layer. So first we start with a batch normalization layer, followed by a ReLU layer. Then we pass the outputs to a weight layer, which is the convolution layer. So we begin by a batch norm layer, followed by ReLU layer. Then we pass the outputs to a weight layer to study the patterns, to study the features, to study new representations. Then we have another batch norm, ReLU, and pass it to another convolution layer. So a important aspect now in the new proposed architecture, which is wide ResNet, we begin with batch normalization layer, followed by ReLU layer, and then we pass it to a convolutional layer to study the spatial features, to study spatial contextual features. But in a normal ResNet architecture, which we studied in the last section, we start with the convolution operation, then we pass its outputs to a batch norm layer. Then we pass the outputs of a batch normalization layer to a ReLU layer to learn complex mappings, to learn complex nonlinear relationships. Then we pass it to another convolutional layer. Then we pass it to another batch norm layer. Okay, so the new idea here is that we start with, we flip the operations, we reorganized the operations into batch normalization layer, then ReLU layer, then we pass into a convolution layer. Very important distinction. And here we have a nice image to show the three pillars, or to discuss the three pillars of the architecture wide ResNet. So we have wide ResNet block pillars. We have width, the width aspect. So not always we have to go deeper. We have a new concept in deep learning. We have a new paradigm in deep learning. We don't just have to go deeper, but always we have to go wider. So don't just go deeper, but also think about going wider. What about if we went wider? Then we have the order of the operations. So we reordered the operations, rearranged the operations, reorganized the operations. We started with a batch normalization layer, followed by a ReLU layer, then a convolution layer. Whereas in the previous ResNet, we started with a convolution layer, followed by batch norm, and then ReLU layer. So we have the order aspect, Then we have parallelism. So parallelism, also we studied the Inception architecture, and we have discussed parallelism operations. The philosophy behind Inception is multi-scale convolutions at one glance, or multi-scale scenes at one glance. So we have parallelized operations happening at the same time, simultaneously. Philosophy in action, enriching the deep-only paradigm. Wide ResNet, widen, don't deepen too much. So here we have a saying, don't deepen too much. Core idea, introduce wider residual blocks. So they introduced wider residual blocks, increased channel count while reducing depth to match parameter budget. So they reduced depth while reducing depth to match parameter budget. Evidence, Zokoriko and Komodakis showed that these are the authors of the paper of this great architecture. So they showed that a 16-layer wide ResNet outperformed 1,000-layer thin ResNets on Cypher and ImageNet with faster convergence and better accuracy. So we have here, they showed that a 16-layer wide ResNet outperformed a 1,000-layer thin ResNet, but thin. Correct that we have 1,000, that's okay, but it was thin ResNet. So the 16-layer but wide ResNet outperformed 1,000-layer thin ResNet on Cypher and ImageNet datasets with faster convergence, which is really great, faster convergence and better accuracy. Nice. Philosophical impact, depth isn't everything. So depth isn't everything. Breadth captures diversity. Also breadth can also help to learn useful, helpful patterns, to learn useful, helpful parameters, weights. So breadth captures diversity. Wide ResNets prove that rich representational capacity can come from width, not solely depth. So the important representational capacity can come from width, not solely depth. This is the first pillar. Wide ResNet, widen, don't deepen too much. Then the second pillar is that pre-activation ResNet, reorder for clarity and flow. Core idea, apply batch normalization, the batch norm layer, batch normalization layer, plus ReLU before convolution within residual blocks rather than after, like in the normal ResNet architecture, to ensure identity paths remain pure. Evidence, Kaiming-He et al., ResNet version 2 showed pre-activation allowed training very deep networks, 1,000 plus layers with improved generalization and stability. So here, Kaiming-He and et al. Showed pre-activation allowed training very deep networks, 1,000 plus layers with improved generalization. Generalization is the ability to generalize across many different input space, and stability. Philosophical impact, the order of transformation matters. So the order matters. the order is important. So the order of the architecture matters. The order of transformation matters. By reordering, rearranging, reorganizing operations, depth becomes cleaner, gradients flow unobstructed, and the network learns residual functions more naturally. ResNext, parallelize through cardinality. Core idea, inspired by Inception. As we said, parallelize means happening at the same time, simultaneously. Okay, so here, parallelize through cardinality, core idea, inspired by Inception. ResNext introduces multiple parallel residual paths, cardinality, within each block grouped convolutions. Evidence: the ResNext paper showed increasing cardinality is more effective than going deeper or wider, or even wider. So increasing cardinality is more effective than going deeper or wider under matched resource budgets, yielding higher accuracy. So they gained higher accuracy with similar complexity. For example, ResNext 50, 32 multiplied by 4D, 4 dimensions, outperformed deeper ResNet 101 and wide ResNet 50. So if you have ResNext 50, 32 multiplied by 4D, outperformed deeper ResNet 101 and also wide ResNet 50 under similar flops budgets. Philosophical impact: cardinality adds a new dimension to network design, parallel expressivity. Instead of stacking and stretching layers, ResNext splits representation into multiple distinct transformations, enriching the network's representational power. So here we have cardinality adds a new dimension. So they added new dimension, added new dimensionality via cardinality to network design. Parallel expressivity, instead of stacking or stretching layers. So instead of stacking or stretching layers, ResNext splits representations into multiple distinct transformations, enriching the network's representational power. So as we said, we have three important pillars. We have the width pillar, which is this pillar here. Wide ResNet, widen, don't deepen too much. So the core idea: introduce wider residual blocks, increase channel count. So they increased channel count while reducing depth to match parameter budget. Secondly, they have order. So they reordered the operations. They started with a batch normalization layer, followed by a ReLU layer, then they passed the outputs to a convolutional layer. Okay? Whereas in the normal ResNet or in the regular ResNet architecture, they started with a convolution layer, weight layer, then passed it to a batch norm layer, then to a ReLU layer. Okay? So you can notice they changed the order. They changed or altered the order of the operations. The third pillar is parallelism. As we said, ResNext parallelized through cardinality. Core idea: inspired by Inception, ResNext introduces multiple parallel residual paths. So they introduced multiple parallel residual paths, cardinality, within each block using grouped convolutions. And as we said, the philosophical impact: cardinality adds a new dimension to network design, parallel expressivity. Instead of stacking or stretching layers, ResNext splits representations into multiple distinct transformations, enriching the network's representational power. Unified philosophical table: philosophical extensions of ResNet. Variant: wide ResNet. Mechanism: increased channel count. So they increased the channel count. Philosophical shift: depth doesn't equal only path to power. So depth isn't the only path to power. Depth isn't the only way towards great artificial intelligence. Depth plus width expands richness. Depth plus width ensures stable gradient optimization process. Depth plus width ensures great optimization experience across the whole neural network architecture. Pre-activation, pre-batch normalization plus ReLU before convolution. Reordering refines depth, preserving identity purity. ResNext grouped parallel residual paths. Cardinality introduces parallelism, maximizing efficiency and expressiveness. So the idea here of pre-activation, they made the batch norm layer and ReLU layer before convolution. And as we said here, the core idea here, apply batch normalization plus ReLU before convolution layer within residual blocks rather than after, to ensure identity paths remain pure. So they ensure that identity paths remain pure. Here we have a philosophical insight. Together, these ResNet variants teach us that model capacity isn't a monolith of depth. It can be a multidimensional, involving width, order, parallelism, and parallelism. By exploring these dimensions, they transformed the ResNet philosophy from a single lane highway of identity-driven depth into a spacious, multi-lane boulevard, where depth, breadth, pre-activation, clarity, and parallel expressivity coexist to yield richer, more efficient learning. And here we have the featured papers, Wide ResNet, or you can name it as ResNet version 2 or ResNext, Wide Residual Networks by Sergei Zokariko and Nikos Komadakis. And here we have the image of the author, Sergei Zokariko. Introduced widen factor to deepen representational richness. So they introduced widen factor to deepen representational richness by widening instead of deepening. So by widening the net instead of deepening it, while wide ResNets improved that faster, stronger, and simpler models could still preserve residual strengths. And here we have the paper. You can read it in your free time. Okay, so if you can view in line. Here we have the paper, the original paper of the architecture wide residual networks. This breakthrough architecture. Abstract. Deep residual networks were shown to be able to scale up to thousands of layers and still have improving performance. As we discussed in ResNet and highway networks, they allowed the training of very deep networks, 900 plus layers, 1001 layer. So deep residual networks were shown to be able to scale up to thousands of layers and still have improving performance. However, each fraction of a percent of improved accuracy costs nearly doubling the number of layers. And so, training very deep residual networks has a problem of diminishing feature reuse, which makes these networks very slow to train. To tackle those problems, in this paper, we conduct a detailed experimental study on the architecture of ResNet blocks, based on which we propose a novel architecture. So they proposed a nice, magnificent novel architecture where we decrease depth and increase width of residual networks. We call the resulting network structure wide residual networks, WRNs, and show that these are far superior even over their commonly used thin and very deep counterparts. For example, we demonstrate that even a simple 16-layer deep wide residual network outperforms in accuracy and efficiency all previous deep residual networks, including 1,000-layer deep networks, achieving new state-of-the-art SOTA results on Cypher, SVHN, COCO, and significant improvements on ImageNet. And you can feel free to read more in this paper. And here we have this image of the architecture. As they said, various residual blocks used in the paper, batch normalization and ReLU precede each convolution, emitted here for clarity, and you can read through this paper in your own free time. Okay, so now we have finished discussing the architecture of wide ResNet. We will go through the architecture which is DenseNet. Okay, so see you in DenseNet. Now let's dive into DenseNet. densely connected convolutional neural network 2016. We have the philosophy as, so the philosophy is every feature matters. Every single feature matters. DenseNet connected each layer to all subsequent ones. So every single layer is connected to all subsequent layers or all subsequent ones, encouraging maximum feature reuse. So here we are encouraging maximum feature reuse and reducing redundancy. It directly tackled vanishing gradients. So they tackled the problem of vanishing gradients and efficiency, deepening representations via dense connectivity. And here we have the image of DenseNet block architecture. As you can see, this is the architecture of DenseNet convolutional neural network. Here we have every single layer is linked to every preceding layer, to every other single layer. Okay, so we have connections, densely connected layers, and these layers also sees every single feature maps produced by the preceding layers. So here we, as we said, DenseNet connected each layer. So here we have layers, okay? So we are connecting or linking each layer to all subsequent ones, encouraging maximum feature reuse. So here the features are reused. We are maximizing the opportunity to feature reuse and reducing redundancy. It directly tackled issues like vanishing gradients, where the gradients become small and small across the architecture, become near zero, and also efficiency. So it is considered a highly efficient architecture, a highly efficient model, deepening representations via dense connectivity. So they integrated dense connectivity into the architecture, dense in connectivity. And as you can see, we have here batch normalization, and then ReLU, and then convolution. And this is adhering to the fact that, as in wide ResNet, they reordered the operations or rearranged the operations, where they started with batch normalization layer followed by a ReLU layer, and then they applied a convolution layer after, not before. As you can see, a 5-layer dense block with a growth rate of k equals 4. Each layer takes all preceding feature maps as input. Philosophy in action, DenseNet's manifestation. Dense connectivity for maximal feature reuse. So as we said, they are maximizing feature reuse. Core innovation, each layer receives inputs from all previous layers via concatenation, not summation. Evidence, as the original DenseNet paper notes, a network of L layers possesses L multiplied by L plus 1 divided by 2 connections, allowing each layer to access the entire history of learned features. So here we are enabling every layer to access the entire history of all the feature maps of the preceding layers. As we said, this is the technique used in this architecture. Each layer is able to access, is able to reach to the entire history of learned features. Philosophical impact, DenseNet treats every intermediate feature map as valuable. So this architecture considers every single feature map. This architecture respects every single feature map, breaking the hierarchy of feature importance. In traditional designs, no feature is discarded. So if you recall, in VGG, in AlexNet, also LeNet, Inception, and also Highway and ResNet, the way to pass data was as the following. We input an image to the architecture, then we apply a set or a series of convolution layers, pooling layers, and batch norm layers, ReLU layers. So the image was going through the architecture, and the following convolution layers just see what the past convolution layer produced. Okay, so there wasn't any technique to densely connect or to link every single layer to see each other's feature maps. But now we are here breaking the hierarchy of feature importance. What is the hierarchy of feature importance? Feature importance is that the very first layers learn simple basic features like edges, textures, lines, dots, circles, shapes, and then the intermediate layers learns whole objects like a person, a person's face, or like eyes, nose, and then the last layers learn the whole picture as a context, as seen. So learn semantic meaning, contextual meaning inside images. But here we are breaking the hierarchy of feature importance. In traditional designs, no feature is discarded, no feature is ignored. Every single feature matters. Alleviating vanishing gradients and enhancing training. So they enhanced training. They enhanced the optimization process, making it more stable. And also they alleviate or mitigated vanishing gradients problem. Core issue: deep nets, as we learned, deep neural networks face several issues. For example, vanishing gradients, making training unstable. So they alleviated this issue by DenseNet's answer: direct connections. So they used direct connections. They utilized direct connections, provide shortcut paths for gradients, reducing attenuation and enabling deeper learning. So they enabled deeper and deeper learning. Philosophical impact: when every feature matters, when every feature is considered important, ensuring they all contribute meaningfully, so every single feature will contribute meaningfully to learning, then this becomes crucial. Dense connections preserve the learning signal across depth. So the dense connections preserve the learning signals, making the signals stronger and stronger, and also keeping the signals active through the entire architecture. There is no any dead signals. There are no any dead signals or any inactive signals. All signals, we are protecting the signals, we are preserving the signals across the whole architecture to be as strong as in the first architecture, to be as active as in the beginning of the architecture. So the philosophical impact: when every feature matters, ensuring they all contribute meaningfully to learning becomes crucial. Dense connections preserve the learning signal across depth. And as we said here, this idea of each layer receives inputs from all previous layers via concatenation, not summation. You have to consider that this is done via concatenation. Parameter efficiency by avoiding redundancy. The third pillar here, or the third cornerstone of this architecture, is that parameter efficiency by avoiding redundancy. Observations: in ResNets, layers may relearn similar features, wasting capacity. So in the architecture ResNet, layers may relearn or may restudy similar features, wasting capacity and also computing power. DenseNet's edge: by concatenating all previous feature maps. So they are concatenating all previous feature maps. Feature maps, as we said, is a name for the result of a convolution. You can refer to the result of a convolution layer, to the product of a convolution layer, as a feature map. So by concatenating all previous feature maps, later layers build upon existing representations rather than recreating them, leading to fewer parameters and higher accuracy and high efficiency. So here we have an important concept, that if you connect every single layer to every other layer, then these layers will build upon existing representations rather than recreating them. But in architectures that don't know what the other layer has learned, then this layer might say, maybe the previous layer didn't learn the edges, maybe the previous layer didn't learn the textures, I will learn them. But if you connect these layers, later layers build upon existing representations rather than recreating them, leading to fewer parameters and higher efficiency. Philosophical insight: feature reuse isn't just functionally elegant, it's resource efficient. So DenseNet not just reusing features, but also it is a resource efficient, resource saving architecture. Empirical success in real tasks: benchmarks DenseNet achieved state-of-the-art SOTA. So state of the art, which is SOTA. If you see SOTA, this is a short for state of the art. Results on Cypher 10, Cypher 100, SVHN, and ImageNet while using fewer parameters, while using a less amount of parameters. Parameters are numerical values inside the net, are numerical values that gets modified, gets altered by the backpropagation and gradient descent algorithm. Analysis papers, follow-up research confirmed that dense connectivity enhances feature propagation and reduces parameter redundancy, all while maintaining high performance. Philosophical validation: when every feature matters, the architecture delivers without compromise. And as we discussed in here, parameter efficiency: in ResNet, layers may relearn similar features, wasting capacity. But in DenseNet, by concatenating all previous feature maps, later layers build upon existing representations rather than recreating them, leading to fewer parameters and also higher efficiency. Here we have philosophical table, DenseNet's proof of concept. Well, the first pillar is that every feature matters. Implementation and evidence: dense connectivity via concatenation. And as we said, this is the formula to count how many links. L multiplied by L plus 1 divided by 2. This gives me the number of links. Robust gradients, improved gradient flow. As we said, always we have to solve the problem of gradient flow. We have to preserve the flow of information. We have to protect the flow of data through the architecture, and also to keep or preserve the signals as powerful as at the beginning of the architecture. So they also incorporated the dense connections, which led to robust gradients, improved gradient flow via direct connections, efficiency through reuse, reduced parameter count versus ResNet at similar accuracy. So similar accuracy, but also reduced parameter count. So with less parameters, but similar accuracy as ResNet, which had a lot more parameters. And then real-world state-of-the-art superior performance on Cypher, SVHN, ImageNet datasets. And if you go here, if you recall, as we said before, evidence: as the original DenseNet paper notes, a network of L layers possesses L multiplied by L plus 1 divided by 2 connections, allowing each layer to access the entire history of learned features. So if you go down now, we have this philosophical insight. DenseNet represented a paradigm shift. So now they introduced a paradigm shift, a new shift in the world of deep learning. DenseNet represented a paradigm shift. It elevated every layer's output into a collective representations, into a collective or accumulative representations, by valuing all learned features equally. So they valued all learned features equally. They valued all learned patterns equally. It fostered a richer, more diverse, and more economical architecture. Rather than discarding or distilling, DenseNet amplifies every contribution, making its philosophy both elegant and practically powerful. Featured paper, DenseNet 2016, and here we have the author of DenseNet paper, Gao Huang, Zhang Liu, and et al. So here they introduced dense connectivity to maximize reuse and efficiency of the features. DenseNet connected everything, not for complexity, but for clarity, where each feature, every single feature matters and none are wasted. And you can feel free to read the paper in your own time. If you click view inline, it will show us the paper, Densely Connected Convolutional Networks. And you can read here the abstract. Recent work has shown that convolutional networks can be substantially deeper, more accurate, and efficient to train if they contain shorter connections between layers close to the input and those close to the output. In this paper, we embrace this observation and introduce the dense convolutional network, DenseNet, which connects each layer to every other layer in a feed-forward fashion, whereas traditional convolutional networks with N layers have L connections, one between each layer and its subsequent layer. Our network has L, as I told you, this formula, L multiplied by L plus 1, so L plus 1 divided by 2 gives me the number of direct connections. For each layer, the feature maps of all preceding layers are used as inputs. So the feature maps of all preceding layers are used as inputs, and its own feature maps are used as inputs into all subsequent layers. DenseNet have several compelling advantages. They alleviate the vanishing gradient problem, strengthen feature propagation, encourage feature reuse, and substantially reduce the number of parameters. We evaluate our proposed architecture on 4 highly competitive object recognition benchmarks, tasks CIFAR 10, CIFAR 100, SVHN, and ImageNet. DenseNets obtain significant improvements over the state-of-the-art on most of them, whilst requiring less computation to achieve. So they required less computation, less amount of parameters, yet performing a significant improvements over state-of-the-art of most of them. So here they achieved high performance. Code and pre-trained models are available at this GitHub repo. So feel free, and here we have the image. You can see every single layer is connected, or is able or is allowed to see all the feature maps produced by the preceding layers, and all the inputs, all the outputs from this layer is connected to every single subsequent layer. And you can read here related work. They have also this image of horse. You can see they inputted an image of horse into a convolutional layer. Then they passed it to a dense block, which is densely connected. Every single neuron, every single unit is connected to every other neuron. Then they pass it to a convolutional layer, then a pooling layer to reduce dimensionality. Then dense block 2, convolution, pooling, dense block 3, so you can choose how many dense blocks you want. Then they have pooling, linear, and they predict this image contains a horse. Hopefully this network predicts that this image contains a horse image, and you can read through that. So here you can see they visualized the target layer. Okay, now we have finished discussing DenseNet. We can move on to Xception, but I want to show you that in Torch Vision, DenseNets are also available in the PyTorch documentation. If you go to models and pre-trained weights, then go down, scroll down, we have here, as I told you, AlexNet, ConvNext, and then DenseNet. If you go to DenseNet, the DenseNet model is based on the densely, so the PyTorch documentation is referring to DenseNet, which means it's a successful architecture. The DenseNet model is based on the densely connected convolutional networks paper, and here we have the variants. We have DenseNet 121, we have DenseNet 161, so 161, they had 161 layers. They have DenseNet 169, and they have lastly DenseNet 201. So these are the variants. These are the types of DenseNet architecture. And in the last section, we also studied about ConvNext. If you go down here, we studied that we have ConvNext. You can also go to ConvNext, and we have here ConvNext Tiny, ConvNext Small, ConvNext Base, ConvNext Large, and feel free to try these models. You can have a look at this documentation. Now we will move on to Xception architecture. So welcome back. Now we will discuss Xception. Xception is short for Extreme Inception. Depth-wise separable CNNs, 2016-2017. So the philosophy is decouple. Here we have the philosophy as decouple spatial and channel representations So here we are separating the spatial learning from the channel cross learning. Decouple spatial and channel representations. Xception distilled Inception, so Xception distilled Inception into depth-wise separable convolutions, showing that extreme modularity could match or surpass conventional convolution layers. Optimizing parameter efficiency, so this is the number one, optimizing parameter efficiency and performance, and also it outperformed the standard convolutional networks. Xception block architecture, we have here a architecture of Xception. As you can see, we have three components: entry flow, we have middle flow, and exit flow. And as you can see, we are entering the input, which is an image. We are entering it or inputting it to a layer of convolution layer. So 3 by 3, the kernel size is 3 by 3 convolution layer, contains 32 filters, and the stride is 2 by 2. So we have stride. Stride is the number of pixels to jump over, the number of pixels to move across. So 2 by 2 stride. And here we are passing it to another convolution layer, and the filter size is 3 by 3. Number of filters or number of kernels, we have 64 filters. Then we pass it to a separable convolution layer. So we have here a separable convolution layer. The kernel size is 3 by 3, and the number of filters is 128 filters. And also passing it to another convolution layer, a standard conv layer, which is of size 1 by 1, and the stride is 2 by 2. And the same thing here, we have a max pooling layer, and you can read the rest. So this is the architecture of the Xception architecture. Philosophy in action, demonstrating decoupling. So we have this concept of decoupling, separating spatial versus channel learning. So we have separated the learning of the spatial dimensions, height and width, from the channel learning. There is a kernel that learns the spatial features, which is height and width, and also we have the channels, the depth, channel learning, a two-step mastery concept. Instead of using a single convolution kernel for both spatial and channel mixing, Xception performs one depth-wise convolution. So as we said here, we have a depth-wise convolution, separable depth-wise convolution. This layer, what is doing? It is doing, or it is applied independently for each channel. So a depth-wise convolution is applied independently for each channel to capture spatial patterns, and point-wise convolution, one by one. Why one by one? To integrate information across channels. So we need to integrate information across channels. Then here we have evidence. Francois Chollet, the author of Xception architecture, Francois Chollet stated that Xception is based on the hypothesis that cross-channel and spatial correlations can be entirely decoupled, can be entirely separated, and each operation can be optimized for its specific role. Philosophical impact. It crystallizes the idea that convolution is two distinct tasks, understanding where and what. So you can understand that convolution is two distinct classes. What is a convolution? A convolution is a mathematical operation that does two distinct tasks. Basically, it's doing understanding where these patterns happen, so where and what. And by splitting them, if you split them, each becomes more effective. So if you try to split the spatial learning from the channel learning, then you are becoming more effective, or the architecture becomes more effective and parameter efficient. The second pillar is extreme modularity with residual structure concept. Xception stacks depth-wise separable convolutions within a clean residual architecture, a linear stack of modules with identity skips. So they also have identity skips akin to ResNet's structure. Philosophical impact, combining decoupling With residual identity paths means modules refine separately land features. So it is refining separately land features without disrupting signal flow. So we are keeping the signal flow as strong as possible. An elegant merge of modularity and depth. So here, if you see the architecture, when after the separable convolution, we are passing it to a max pooling layer. Then we have some residual connection here. We are taking the output of this convolution layer and combining it with the output of the max pooling. So we have some kind of here residual connections. Okay, identity residual connections. Why? To preserve the signal power to be as strong as possible throughout the whole architecture of Xception. And here you can see we are passing the output of this residual connection. We are passing it to a separable convolution layer with 3x3 kernel size, and notice that we have now an increasing number of filters. We have 256 filters, and also passing it to a convolution, to a normal convolution layer. So we have two types of layers. We have separable convolution and we have convolution. Then the same thing, we are passing it to a max pooling layer. This max pool layer reduces the spatial size, reduces or decreases the spatial dimensions, and we are taking the output of this convolution and combining it with the output of the max pooling and passing it again to another separable and convolution layer. So here we have a pattern. If you go down here, efficiency without sacrificing power. Efficiency without sacrificing power. Evidence: Xception achieves slightly better performance than Inception version 3. Inception version 3 on ImageNet, and significantly outperforms it on GFT while using the same number of parameters. So while using the same number of parameters, Xception, this new architecture, achieves slightly better performance than Inception version 3 on ImageNet and significantly outperforms it. This referred to the Inception version 3, outperforms it on GFT. Further validation: the architecture became the inspiration for MobileNets, which we have later. So here we have a chronological order. First we have Inception, then after a while we had this nice architecture Xception, which decouples the spatial learning from the channel learning. Then we have MobileNets. MobileNets inspired its separable convolution idea from the Xception architecture. Okay, so now we have this. The architecture became the inspiration for MobileNets, showing separable convolutions value on resource constrained devices. So MobileNets showed separable convolutions value on resource constrained devices. So if you have devices that are of resource constraint, if you don't that much power, computing power, if you don't that much memory storage capacity, then you have to think about using MobileNets. Why? Because they are so efficient, really efficient for resource constrained devices. Philosophical impact: true modular separation leads not just to theoretical elegance but also to practical gains: efficient, expressive, and scalable. And if you read here about the pillars, we have the first pillar, which is decouple, spatial, and channel. So we separated spatial and channel. We splitted the spatial learning, so height of the image, the width of the image, and the channel learning, depth-wise plus point-wise convolutions. 2. Modular and with residual paths. So this architecture is modular with residual paths. Linear stack plus identity shortcuts. Efficiency and performance: outperforms Inception version 3 with GFT with the same parameters. Enabling compact models. Inspired MobileNets, which we'll talk about later. So inspired MobileNets for on-device inference. So if you want to do on-device inference, you may look into MobileNets. And now let's read the philosophical insight. Xception did more than refine Inception. So Xception did more than refine Inception. It offered a purer conceptual split between what a filter detects and where it sees it. So what a filter detects, this is the channel learning, and where it sees it. This is the spatial learning. So in terms of the height and width. So in terms of height and width, this is the spatial learning, where it sees the features. And what a filter detects in terms of the channels. So the third dimension, the channels, the colors, what a filter detects. By decoupling spatial and channel processing and trying them with residual identity pathways, it delivered both elegance and efficacy. This modular philosophy proved practical in high stakes benchmarks and seeded future lightweight architectures like MobileNets, reaffirming that extreme modularity with clarity pushes the frontier of deep learning. And here we have the author of this great paper, Xception, Francois Cholet, and this is the image of Francois Cholet. Deep learning with depth-wise separable convolutions, and feel free to read the paper in your own time. We shouldn't force one operation to do two jobs. We shouldn't force one operation, convolution operation, to do two jobs. When spatial and channel processing are disentangled, deep learning flows cleaner and faster. And here we have the paper of Xception module. We can click view in line, then you can read through this paper. So Xception, deep learning with depth-wise separable convolutions, and the author is Francois Cholet. And feel free to read through this. So here, abstract, we present an interpretation of Inception modules in convolutional networks as being an intermediate step in between regular convolution and the depth-wise separable convolution operation. A depth-wise convolution followed by a point-wise convolution. In this slide, a depth-wise separable convolution can be understood as an Inception module with a maximally large number of towers. This observation leads us to propose a novel, deep convolutional neural network. So this is a novel, deep convolutional neural network architecture inspired by the Inception, where Inception modules have been replaced with depth-wise separable convolutions. So Francois Cholet has replaced Inception modules have been replaced with depth-wise separable convolutions. We show that this architecture, dubbed Xception, slightly outperforms Inception version 3 on the ImageNet dataset, which Inception version 3 was designed for, and significantly outperforms Inception version 3 on a larger image classification dataset, comprising 350 million images and 17,000 classes. Since the Xception architecture has the same number of parameters as Inception version 3, the performance gains are not due to increased capacity, but rather a more efficient use of model parameters. And feel free to read through that. You can see here we have the architecture, concatenation, we have a convolution 3x3, 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 then we have this convolution 1x1. Okay, so input goes through this layer, then it passes from this convolution 1x1, it passes the output to 3 layers in parallel, convolution, 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 3x3, 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 and then we concatenate the outputs. Here, output channels, okay? And you can look more through these architectures in your own time, okay? But now we have finished discussing Xception. We will move on to MobileNets. So let's discuss MobileNets. Now we will discuss MobileNet 2017. The core idea behind MobileNet is that what do we need when we have almost nothing? So its philosophy is, what do we need when we have almost nothing? So if we don't have that much computing power, if we don't have that much memory storage, what do we need when we have almost nothing computing power? We don't have any computing power, we don't have any memory storage, we don't have the capabilities or the capacity of the powerful computing systems. It's not in excess where intelligence matures, but in constraint where it is refined. So it's not in excess where intelligence matures, but in constraint where it is refined. And as you can see here in the image, we have the architecture of MobileNet architecture. The white layers are convolution plus ReLU layers, and we have the purple layers are max pooling layers. So you have max pool layer to reduce the spatial dimensions and to reduce the risk of overfitting. And this layer, which is in the color of turquoise, we have average pool layer, average pooling layer, and then we pass it to the final fully connected layer and output logits. How the architecture aligns with the philosophy. The first pillar is that depth-wise separable convolutions. So here we have the idea of depth-wise separable convolutions. So depth-wise separable convolutions, deconstruct to reconstruct. A standard convolution fuses spatial filtering, and feature combining in one heavy-handed step. So if you use the standard convolution layer, then you are fusing spatial filtering and feature combining in one heavy-handed step. MobileNet asks, do we really need both at once? So do we really need both of these tasks at once? Instead, it separated the process into depth-wise convolution. So we have depth-wise convolution, one spatial filter per channel, the minimalist's lens. And we have point-wise one-by-one convolution, reconstruct global understanding, but only when essentials but only after essentials are isolated. So the first pillar is depth-wise separable convolutions. Here, if you go down to the architecture, you will see that depth-wise separable convolutions, the philosophical value, separation of concerns, it led to about 9x fewer flops than standard CNNs. So 9x fewer floating point operations than standard CNNs. The second pillar is that, and here we have an effect, reduces computations by about 9x with only marginal accuracy loss. To build wisely, deconstruct first. The second pillar is that width and resolution multipliers, minimalism with control. 2 hyperparameters. So hyperparameters are external configurations that machine learning engineers need to set. Machine learning engineers need to set its values by themselves. It's not learnable. So 2 hyperparameters let us scale the model not by adding more, but by doing less with more intention. Width multiplier. So we have width multiplier alpha thins the network. So this hyperparameter, it thins the network, fewer channels, leaner computation. So when you adjust the alpha hyperparameter, then you are thinning the network, thins the network, which leads to fewer channels. When you have a thin network, that means it has few channels, and then it leads to leaner computation. Resolution multiplier beta reduces spatial resolution, sees less but perhaps sees enough. So maybe the architecture sees less of the resolution of the image, but perhaps sees enough samples, sees enough pixels to understand the context and the scene going on in the image. Don't deepen the network, tighten its belt. So maybe in some cases we don't need to go deeper. What if going deeper is not the best solution? So don't deepen the network, tighten its belt. Third pillar, modular structure, simplicity as strategy. MobileNet's repeating pattern of depthwise, and then we have pointwise. So we have a pattern of depthwise going to pointwise, depthwise. After the pointwise, we have after depthwise, we have pointwise created. Fast inference via matrix optimized general matrix multiplication operations. So GEMM is short for general matrix multiplication operations, and ops is short for operations. Fast inference via matrix optimized. deployment ease on mobile and embedded systems. So MobileNet is a family, if you return here, MobileNet is a family of convolutional networks. So it is a family of convolutional neural networks that best suits mobile devices, embedded systems like phones, mobile phones, and also the cameras, and a lot of device constraint or resource constrained devices. If you have resource constrained devices, then you may want to look into MobileNet. Its philosophy is, again, what do we need when we have almost nothing? So for example, what do we need when we want to run a network on the mobile device, or to run a network on a drone, or for example on a like any resource constrained devices? Then we want to use, or we need to use, MobileNet architecture. Here we have this MobileNet repeating pattern of depthwise, pointwise created fast inference via matrix optimized GEMM operations, deployment ease on mobile and embedded systems, adaptability to tasks like SSD detection, deep lab segmentation, FaceNet distillation, a 28-layer deep network built on just 2 atomic operations. So we have a 20-layer deep network. MobileNet is consisted of 28-layer deep network built on just 2 atomic operations. Backpropagation plus RMS prop. So backpropagation is a mathematical algorithm that computes the gradients of the loss function based on the weights, plus RMS prop, root mean squared propagation, lead to training efficiency. So when you combine backpropagation with RMS prop, then that leads to training efficiency. Why? MobileNet replaced vanilla SGD, stochastic gradient descent, with RMS prop, root mean squared propagation, adapting learning to constrained models. Because if you want to train a network that adapts to constrained models, then you may have to choose RMS prop as an optimizer instead of SGD, instead of vanilla SGD. In small capacity models, every gradient counts. Momentum of learning. So in small capacity models, every gradient counts, and RMS prop meets this condition. Momentum of learning must be guided with more care than brute force. So momentum of learning must be guided with more care than brute force. And here we have this table or summary. Feature: depthwise separable convolution, philosophical values, separation of concerns. It led to about 9x fewer flops than standard CNNs. So here, if you recall, the first pillar was depthwise separable convolutions. So Xception inspired MobileNets. The Xception architecture, which introduced depthwise separable convolutions, inspired later an architecture of MobileNet. Why? As we said, a standard convolution fuses spatial filtering and feature combining in one heavy-handed step. MobileNet asked, do we really need both at once? Instead, MobileNet splitted the process into depthwise convolution, meaning one spatial filter per channel. So we have one filter per each channel, the minimalist's lens, and we have pointwise one-by-one convolution to reconstruct. So the one-by-one convolution reconstruct global understanding, but only after essentials are isolated. The second pillar here is width resolution multipliers. As we said, they introduced 2 hyperparameters, the width and resolution multipliers: scalable minimalism, adjustable speed, accuracy trade-offs. So we have adjustable speed. It leads to adjustable speed, accuracy trade-offs. The second pillar that we talked about was the width and resolution multipliers. So 2 hyperparameters let us scale the model not by adding more, but by doing less. So MobileNet redefined deep learning, that maybe we don't need to add more layers, maybe we don't need to go deeper, maybe we will need to do less. we will need to build wisely, to deconstruct first. So to build wisely, deconstruct first, but by doing less with more intention. Width multiplier, alpha, width multiplier thins the network, fewer channels, so we had fewer channels, leaner computation. Resolution multiplier, beta, reduces spatial resolution, sees less but perhaps sees enough. So maybe the image is less in size, but perhaps it's enough for the network to make predictions, to classify. So don't deepen the network, tighten its build. The third pillar is modular factorized design, clarity in constraint, GEMM friendly. So MobileNet is general matrix multiplication friendly, easier deployment on mobile and low power devices. RMS prop optimization, root mean squared propagation optimization, momentum in scarcity, stable training in lean networks. So as we said here, the third pillar is modular structure. MobileNet has a modular structure. Simplicity as strategy. They chosen simplicity as a strategy to build their architecture. MobileNet's repeating pattern of depthwise, pointwise created this ease of deployment on mobile and embedded systems, like the, as we said, cameras, or like the systems that don't have that much computing power, like mobile phones. So it's suitable for these, and also for cars, autonomous cars. And we have here distillation compatibility, wisdom over brute force. Outperformed SqueezeNet, also rivaled AlexNet. Conclusion: from survival to sufficiency, MobileNet reframed the question, not how deep can we go. So MobileNet redefined deep learning by the core idea is that we don't have to go deeper. Not how deep we can go or can we go, but how little do we need to see clearly. How much enough layers do we need to compute less, but also to get yet powerful trainable network. So, but how little do we need to see clearly? Just as Ashish Vaswani declared in 2017, attention is all you need. MobileNet whispers from the edge of minimalism, efficiency is all we could afford. Efficiency is all we could afford. So we turned it into elegance. So here, if you remember, the second pillar was width and resolution multipliers. To hyperparameters let us scale the model not by adding more. So the idea here is not to add more layers, but by doing less operations or less layers, yet a powerful and also highly efficient network. Philosophical insight: MobileNet redefined what it means to be powerful in deep learning, not by increasing capacity, but by embracing constraint, by focusing on constraints. It showed that when every operation must justify its existence, elegance emerges. This minimalist philosophy became a cornerstone for AI on the edge, mobile inference, and embedded intelligence. And we have embedded intelligence in, this is a new concept or new trend in AI. Embedded intelligence is the intelligent models now are not working just from clouds, but also are embedded inside the systems, like mobile phones, like the cameras themselves. Featured paper, MobileNet 2017, MobileNets, efficient convolutional neural network. So as we said, MobileNets is a family of convolutional neural networks, efficient for mobile vision applications, by Andrew G. Howard and et al. So here we have the image of the author, Andrew G. Howard. Google Research introduced depthwise separable convolutions and scalable hyperparameters. And they said, we present a class of efficient, meaning a group of efficient models based on a streamlined architecture that uses depthwise separable convolutions to build lightweight deep networks. And here we have the paper. You can read it in your own free time. So view inline, you can read the paper, MobileNets, efficient convolutional neural networks for mobile vision applications, by Andrew G. Howard and at all. Here we have the abstract as we present a class of efficient models called MobileNets for mobile and embedded vision applications. So as we said, there was a need to run neural networks, large neural networks on devices that doesn't have that much computing power, that doesn't have or doesn't utilize that much memory storage. So they had to create a compact, small network that fits into these devices. So here, called MobileNets for mobile and embedded vision applications. MobileNets are based on a streamlined architecture. So real-time architecture that works in real time, that uses depth-wise separable convolutions to build lightweight, deep neural networks. They introduced two simple global hyperparameters, as we said, alpha and beta, with the width controller or multiplier and the resolution multiplier that efficiently trade off between latency and accuracy. These hyperparameters allow the model builder to choose the right sized model for their application based on the constraints of the problem. We present extensive experiments on resource and accuracy trade-offs and show strong performance compared to other popular models on ImageNet classification. We then demonstrate the effectiveness of MobileNets across a wide range of applications and use cases, including object detection, figurine classification, face attributes, and large-scale geo-localization. So feel free to read through this architecture, and you can see here they have this architecture in this table. So this is the MobileNet body architecture. They have here convolutional layers, as you can see, DW meaning depth-wise convolution, and S is short for stride. Stride, as we said, is a hyperparameter. Stride is a hyperparameter in CNNs that defines how much pixels to jump over, how many pixels to move across. If you define it as 2, then the convolution kernel will move by 2 pixels each time, and if 1, it will move by 1 pixel. And here we have a series of convolution layers until we have this fully connected. So we have average pooling layer, average pool that reduces the size into the overall trend, into the overall features, and then pass into a fully connected layer. Then we pass into a softmax layer to classify, so the classifier head. And if you go down here, you can read more through the architecture. And also, if you go to Torch Vision models library, you will see MobileNets are included in the Torch Vision library. If you scroll down, here we have for classification, which is classification models. The following classification models are available with or without pre-trained weights. So you could use these architectures with or without pre-trained weights. And here we have MobileNet. We have MobileNet version 2, MobileNet version 3. You can choose MobileNet version 2. And we have here the MobileNet version 2 model is based on this paper. And if you go down, you can use this MobileNet version 2 model. So now we have finished discussing this model. We will move on to EfficientNet and beyond 2019 plus. Now we will discuss EfficientNet. EfficientNet is a family of convolutional neural networks. 2019 philosophy: scale in balance. So this EfficientNet is based on scale in balance, balancing the scales. EfficientNet introduced compound scaling, jointly tuning depth, width, and resolution together based on principled search. It emphasized that balanced scaling, not just brute force, yields the most efficient and performant models. And here you can see the architecture of EfficientNet architecture as shown in the image. We input an image of size 224 by 224 by 3 canal channels. So the height of the image is 224, the width of the image is 224, and then we have 3 canal channels, and we input this image into a series of convolutional layers, and then we output feature map of this size 7 by 7 by 320. and MB convolution is a block, is called MB convolution. This block is a mobile friendly convolution block. So MB convolution, we have this MB convolution block. Philosophy in action, scaling in balance, in balance, principled compound scaling. So as we said, EfficientNet is based on principled compound scaling. The core of innovation, rather than arbitrarily boosting model dimensions, so rather than just arbitrarily boosting model dimensions, just the width, just the depth, EfficientNet introduced a compound coefficient phi to simultaneously scale depth alpha, so the depth of the network, number of layers alpha, width beta, so number of channels, number of neurons, number of filters is called width, and we have resolution, which is the input image size, under the constraint alpha times beta raised to the power 2 times gamma raised to the power 2 equals around about 2. Philosophical impact. This approach embodies balanced evolution, balanced scaling, recognizing that depth, width, and resolution are interdependent. There is a certain correlation between depth, width, and resolution, and must grow together. So these three dimensions, instead of just growing the depth, instead of just increasing the width, we are increasing all of the three dimensions. We are increasing depth, width, and resolution simultaneously, uniformly, in a consistent way, are interdependent, and must grow together for truly efficient scale up. So to truly make the architecture efficient, to truly make the architecture efficient scaled up, we have to at the same time increase depth with width with resolution, and must grow together for truly efficient scale ups. The second pillar, empirical validation. Key results: achieved state-of-the-art accuracy while being 8 times smaller and 6 times faster than prior CNNs. So 8 times here, we have 8 times smaller and 6 times faster than prior CNNs. Example, EfficientNet P7 reached 84.3% top 1 accuracy on ImageNet, which is a state-of-the-art result. This is the first time we reach 84.3% top 1 accuracy on ImageNet. Ablation studies, scaling only one dimension led to diminishing returns. So when you scale just one dimension, for example depth or width or resolution, scaling one dimension led to diminishing returns. Compound scaling consistently outperformed isolated scaling paths. The third pillar here, integration of modern modules. MB convolution plus squeeze and excitation. EfficientNet builds on the mobile-friendly NB convolution block and enhances feature learning with squeeze and excitation layers. NAS enhanced baseline. EfficientNet, so NAS is short for Neural Architecture Search. NAS enhanced baseline. Efficient B0 was discovered via Neural Architecture Search, NAS, ensuring efficiency from the ground up. The fourth pillar is that the broader legacy, architectural influence, inspired successes like EfficientNet version 2, MobileNet version 2, MobileNet version 3, and ResNet RS. Even transformer-based scaling, for example, Vision Transformers, adopted the philosophy of balanced growth. Real-world impact, widely adopted in mobile, edge, and cloud deployments where efficiency matters as much as raw accuracy. So the philosophical table here is that EfficientNet philosophical manifested pillar. First of all, we have the first pillar, which is balanced scaling. Compound method, phi with alpha. Alpha, as we said, if you recall here we have depth is alpha. So alpha is a parameter that controls the depth. Beta is a parameter or coefficient that controls the width. And gamma is a parameter that controls the resolution. So we have alpha, beta, gamma. Very important. 3 coefficients introduced in the paper EfficientNet. So compound method phi with alpha, beta, gamma constraints. Efficiency and high accuracy. B7 reaches 84.3 top 1 accuracy with 8x fewer parameters. Ablation confirmation. Compound scaling is more than single axis scaling, or compound scaling is best than single axis scaling. So rather than just scale one axis, whether it was depth or width or resolution, why don't we scale all of them? Why don't we scale all the 3 dimensions simultaneously at one glance? Built from efficient modules, MB convolution plus SE blocks, NAS designed B0. So built from efficient modules. We have previous models like MobileNets that introduced MB convolution. We have CNets, which introduced SE blocks, and we have NASNets, which introduced neural architecture set designed B0. Inspired successes: it inspired EfficientNet version 2, EfficientNet version 2, ResNet RS, even transformer scaling. Philosophical insight and even transformer scaling. Philosophical insight: EfficientNet taught the deep learning community that scaling is an art of balance, not mere brute force. True model excellence emerges when depth, width, and resolution grow in symphony, a principle now central to architectural design in efficient, deployable AI systems. Featured paper, EfficientNet 2019, EfficientNet Rethinking Model Scaling for CNNs. So here we have the author, Mixing Tan and Cook V. These are the 2 authors of this paper, and here we have the image of the author, who is Mixing Tan. Depth, width, resolution, scaling unified by coefficient phi. Instead of scaling arbitrarily, we scale all dimensions. We scale every single dimension, width, depth, and resolution, in a principled way, in a uniformed way. Depth, width, and resolution guided by a single factor, guided by a single coefficient. And here we have the paper, the link to the paper, view inline, or the button that shows the paper in a pop-up mode. EfficientNet Rethinking Model Scaling for Convolutional Neural Networks. So we are here rethinking model scaling for convolutional neural networks. This is the title for EfficientNet paper. And here by Mixing Tan and Cook V. Lee. Abstract: convolutional networks, ConvNets, are commonly developed at a fixed resource budget and then scaled up for better accuracy if more resources are available. In this paper, we systematically study model scaling and identify that. So here we inferred that they focused on scaling. This paper is focusing on the scaling aspect. Study model scaling and identify that carefully balancing network depth, width, and resolution can lead to better performance. Based on this observation, we propose a new scaling method that uniformly, that consistently scales all dimensions of depth, width, resolution using a simple yet highly effective compound coefficient. We demonstrate the effectiveness of this method on scaling up MobileNets and ResNet. So they demonstrated the effectiveness of this method by scaling up MobileNets and ResNets. To go even further, we used neural architecture search, which is NAS, neural architecture search, to design a new baseline network to scale it up to obtain a family of models called EfficientNets, which achieve much better accuracy and efficiency than previous ConvNets. In particular, our EfficientNet B7, the last model, we have a range that ranges from B0 to B7. We have B0, B1, B2, B3, B4, B5, and B6, B7 achieves, but B7 achieves state-of-the-art 84.3% top 1 accuracy on ImageNet, while being 8.4x smaller and 6.1 faster on inference than the best existing ConvNet. Our EfficientNets also transfer well and achieve state-of-the-art on CIFAR 100, 91.7 accuracy and also on the flowers dataset, 98.8% accuracy, and 3 other transfer learning datasets with an order of magnitude fewer parameters. Source code is available at this repo. And if you go down here, you can see that here we have a comparison between, we have now Inception version 2, we have ResNet 50. So you can see here we have ResNet 50, we have ResNet 152, and we have Inception ResNet version 2, because we have Inception version 3 is combined Inception with ResNet version 2. And we have ResNext, also we have Xception, DenseNet, Inception, NASNet, and here we have EfficientNet. You can see that EfficientNet here is the best performing model. We have here the x-axis represents number of parameters in millions. So here you can see that EfficientNet is about between 60 and 80 million parameters, and here with the accuracy here you can see highest accuracy. It leads to here the y-axis represents ImageNet top 1 accuracy. So we have the highest accuracy versus a less amount of parameters compared to other models, compared to the counterparts. Okay, so this image is really important. You will see it in many different places, comparing the EfficientNet to other different previous convolution nets. And if you go here down, they said that in this paper, so here they said in this paper we want to study and rethink the process of scaling up conv nets. In particular, we investigate the central question: is there a principled method to scale up convolution nets that can achieve better accuracy and efficiency? Our empirical study shows that it is critical to balance all dimensions of network: width, depth, resolution, and surprisingly such balance can be achieved by simply scaling each of them with constant ratio. Based on this observation, we propose a simple yet effective compound scaling method. So they have a compound scaling method. Unlike conventional practice that arbitrarily scales these factors, our method uniformly, consistently scales network width, depth, and resolution. So we have here in this image, you can see here baseline. So this is the baseline architecture. Here we have B, width scaling. So they scaled width, the width of the network, and here they've scaled the depth. So the depthness here, depth scaling, going deeper, and here going wider, and here they have resolution scaling, and here they combined it, they accumulated them into compound scaling. Okay, and resolution with a set of fixed scaling coefficients. For example, if you want to use n2 raised to the power n times more computational resources, then we can simply increase the network depth by alpha n, width by beta n. So if you want to increase the depth, you want to use alpha. If you want to increase the width, you want to use beta. And image size by gamma, where alpha, beta, and gamma are constant coefficients determined by a small grid search on the original small model. And here they said that intuitively the compound scaling method makes sense, because if the input image is bigger, this is intuitive, because if you have a larger input image, if you have a large and big input image, if the input image is bigger, then the network needs more layers to increase the receptive field and more channels to capture more fine-grained patterns on the bigger image. Okay, so now you can read in your own time all of the paper, but by finishing that, we have finished discussing the EfficientNet architecture. The main idea behind it is that they've scaled up all the dimensions, width, depth, resolution, and they got better performance. And here you can see that they also have the comparison between the Cypher 10, Cypher 100, and also the BirdSnap, Stanford cars. These are different datasets that they've used to test the model. Okay, so now we will go to, if you go to Torch Vision models, and then go to models, you can see that they have here, also they have in the classification models, they have EfficientNet. And EfficientNet, as we said, the EfficientNet model is based on the EfficientNet rethinking model scaling for convolutional networks Here we have EfficientNet B0, EfficientNet B1, EfficientNet B2, B3, B4, B5 until we have EfficientNet B7. And you can go to the paper from here by clicking this. Now we will move on to VIT, Vision Transformers. So see you in the VIT Transformer section. Now we will discuss transformers and vision transformers, VIT models. Philosophy: beyond convolution, preserve identity. So now we are going beyond convolution, beyond convolutional neural networks, and also preserving identity. So yet preserving identity, bringing ResNet's skip connections forward. Transformers rely on self-attention mechanism blocks with residuals to build global context efficiently. VITs extend this to vision, blending patch embedding with identity preservation, pushing paradigms even further. So we have brought the ResNet's skip connections forward into vision transformers. In vision transformers, we utilized skip connections, residual connections, or the bypass connections, allowing the network to remember the original data shape. Transformers rely on self-attention blocks, but now we have transformers, and the transformer architecture relies on self-attention blocks with residuals to build global context efficiently. So we are building now global context, not just local context. Now we are learning global context efficiently. VITs extend this to vision, blending patch embedding, and we segment the image into patches with identity preservation, pushing paradigms even further. And now we have this image of transformers block architecture. First, we start with an image. As you can see, we have an image, and we segment. The first step is to segment the image into patches, is to split the image into patches. As you can see, we are splitting them into patches and then passing these patches. So when we deal with NLP, natural language processing, with text problems or text domain, we have to segment the text into tokens, into sub-tokens. For example, based on the words, or based on the letters, or based on these sub-words. But here we have an image. Here we have a photo. So we have to segment the photo into segments, into patches. It's called patches. And then after we segment the image into patches, into sub-patches, we pass them to a linear projection of flattened patches. So we flatten them using a flattened layer. Then since transformers doesn't have a built-in mechanism to learn context or to learn the positional meaning, we have to implement or include the position embedding. So we have to include positional embedding to preserve the position of the words, or to preserve the position of the patches. Here we are dealing with images, dealing with vision domain. So we want to preserve the context of the image, the context of the patches, the order, to preserve the order or to protect the order of the patches. And we have also extra learnable class, which is CLS token, extra learnable embedding class. And this extra learnable class, we have to include it in order to make the process of learning more stabilized. Then we pass these flattened patches into, plus with the positional embedding, we pass it to a transformer encoder. And transformer encoder, if you scroll down, this is the architecture of the transformer encoder. And here we can see that we have this image. If you scroll down, we have this image of transformer encoder. Here we start with inputs. So we input some inputs, like for example, let's pretend we are dealing with text domain. I went to school yesterday. So we input this sentence into the architecture. Then we have to convert these inputs. We have to segment these inputs into tokens. So I is a word, went is a single word. So we tokenize it. We utilize the process of tokenization to tokenize the sentence into subtokens, and then pass these inputs, these tokens, into input embedding layer to convert them from a tokens into embeddings, to map these tokens into dense vectors. And then we add or preserve the positional meaning, the positional encoding, via preserving the order of the words or the order of the meaning, in order to have meaningful patterns or meaningful words. Then we pass it to a transformer encoder here, multi-head attention. So we apply the mechanism of multi-head attention, which contains of 3 parameters, which is the Q, and we have the K, and we have V. These are 3 like windows or like matrices that is learned via multi-head attention. Then we pass it to another layer, which is add and norm, the normalization layer, and this is a residual connection here. We are preserving the identity of the sentences or of the text by passing the identity or passing the real text to the add and norm layer to learn the identity and to preserve the shape of the text, to make the layers remember the original format of the text or of the embedding vectors. And then we pass it to a feed forward layer to learn more fine-grained detailed patterns. So we pass it to a feed forward layer, and then we pass it to another add and norm layer. So we apply another residual connection here to preserve the real identity of the data. Then we pass it to a decoder layer. But here, if you notice, we don't have a decoder in VIT. VIT just have encoder transformer. Why? Because we don't want to talk. We don't want to generate text. Here we want to classify, for example. So classify images as something or another. So we don't need a decoder to decode something or to generate. We just need to learn the patterns. So we have just a transformer encoder. After this transformer encoder, we pass the outputs into a multi-layer perceptron head. So we have MLB, multi-layer perceptron head, and then this head classifies into classes. So we had, this is a classifier head. So it's called a classifier head. As the classifier head, it classifies into different classes like bed, ball, car. This is like a simple linear layer, multi-layer perceptron head that classifies into different classes. So as a revision, we said that transformers and vision transformers, the philosophy beyond convolution, going beyond convolution, preserve identity, right? We are going beyond convolution, but yet preserving identity, bringing ResNet's skip connections that we mentioned here, as we said in the architecture of this multi or of this transformer architecture. We are preserving the identity via these skip connections. So we have, this is a skip connection that preserves the identity, and now we have also, after this ResNet skip connections, forward transformers rely on self-attention blocks, which we have here. So here we have the self-attention blocks, multi-head attention, that learns the relationships, the patterns, the features inside text or in the dense embedding in the dense embedding vectors, and then it passes it to another add and norm layer. This normalization layer normalizes the outputs and then pass it to another feed forward layer. Then we have another residual connection. So after we pass it to a feed forward layer, we also preserve the identity, preserve the real data, and pass it to another, and combine it with the outputs of the feed forward layer. And we repeat this block several times, nx. So you may want to repeat it 3 times or 2 times or just 5 times, whatever you choose. And here we have, if you see, the transformer encoder learns these patterns and map them into the classes. Philosophy in action, transformers and VIT. So skip connection sustain depth and stability. Skip connections preserve the depth and also preserve the flow of the information, making the process of flowing the information stable and stabilized, and also stability is also preserved via skip connections. Concept: just like ResNets, transformers use residual connections. Transformers utilize residual connections around both multi-head self-attention MSA, so multi-head self-attention, and feed-forward FFN sublayers. Evidence: residual paths are essential to gradient preservation in deep transformer stacks. Residual connections are used around self-attention mechanism to improve gradient flow and enable the training of deep networks. So here, as we said, the purpose of the residual connections is to preserve the flow of the gradients. Transformers use residual connections around both multi-head self-attention and feed-forward layers, sublayers, as in here. So as it uses the residual connections around the multi-head self-attention and also around the feed-forward network layer. So we have two residual connections here, as mentioned in the sentence here. Then evidence: residual paths are essential to gradient preservation in deep transformer stacks. So to not make the signal get weaker and weaker, to keep the signal get powerful and stronger across the whole architecture. When you repeat this block several times, it may forget what the real data looked like. It may forget what it was learning. So to make these layers go deeper and deeper safely, with remembering the features, with remembering the essential patterns, then we have to preserve the identity, or to make skip connections to make the layers remember what it is learning. So we're not just learning patterns in a feed-forward fashion, but also in a way that makes the layers remember what it was learning in original way. Residual connections are used around the self-attention mechanism to improve gradient flow and enable the training of deeper networks. Philosophical impact: even without convolutions, identity preservation remains fundamental. Depth is enabled by allowing information to flow undisturbed. The second pillar here is global context via self-attention. Concept: replacing local convolutional receptive fields, self-attention provides global inter-token relationships. So the transformer architecture, or the self-attention mechanism, provides us with the feature of global inter-token relationships. So it layers the relationships between inter-token dependencies, capturing context across the entire input. Unlike convolution, which learns local patches, when it slides the filter across the image, then it learns just what the kernel covers. But here, replacing local convolution receptive fields, self-attention provides global inter-token relationships, capturing context across the entire input. Evidence: transformers capture long-range dependencies using self-attention, allowing tokens to attend to all others directly. And here we are dealing with images, so allowing patches to attend to all others directly. VITs, or vision transformers, tokenize or patchify images into patches, applying attention to model structure like in language. Philosophical impact: the model preserves identity while enriching signals with holistic global understanding, a radical departure from locality. So now we are moving from locality into globality via using the transformer architecture. So the model preserves identity while enriching the signals. So we don't want the signals to die. We don't want the signals to die. This is an undesirable behavior. When the signals get weaker and weaker, when the signals get inactive, we need to keep the signals, to protect the signals to be as informative as the architecture needs to update the weights. The signal is the gradient error, and the gradient error informs the gradient descent optimizer to update the weights, whether to increase the weights or decrease the weights. So here we are enriching signals with holistic global understanding across the whole tokens or whole patches. identity plus attention, depth and globality combined. Concept: VIT's architecture follows output equals X plus multi-head self-attention, and we pass the X applied layer norm. So we take X, which is the input, and apply a layer normalization operation, and then pass the output to a multi-head self-attention, and we combine this transformed version, we combine it with the identity, with the real X, with the identity, and then we assign it to output. Output equals Y. Now we take the Y plus f of n, and then we pass to it a layer norm, and then we pass Y. So we are taking Y, applying the layer normalization operation, and then pass it to f of n, and also take this transformed, we are taking this transformed version and combining with the real output from this operation. So the same as this is a mathematical way of this architecture. So we are taking X, passing it to a multi-head attention, applying the three matrices K, V, Q, and then also preserving the identity, preserving the real data into here. Add a norm, and then we take the output from this. So now we have Y. This is Y here, and then we combine the Y, the real Y that goes from here to here, pass it to here, and we combine it to the output of the feed forward layer. Philosophical impact: the combining of global context, multi-head self-attention with residual identity keeps models deep, expressive, and trainable, and also keeps models stabilized or stable and more robust across the whole architecture, from the beginning of the architecture to the end of the architecture, making the later layers refreshable with what X looks like. Empirical strength in vision tasks concept: when trained on large datasets, VITs outperform CNNs, capitalizing on their global receptive field. So transformers benefits from their global receptive field and also outperformed the CNNs. Evidence: VIT attains excellent results compared to state-of-the-art convolutional networks while requiring substantially fewer computational resources to train. Residual attention hybrids like RSA VIT preserve local detail while modeling global structure. Philosophical impact: identity preservation enables depth and expressiveness, enables depth and going deeper and deeper, and also expressiveness, while attention grants global perception. And then we have hybrid and successor models concept. Many computer vision, so CV is computer vision, many computer vision models fuse convolutions and attention. In other words, many computer vision models use both convolutions and attention, or combines both convolutions plus attention. For example, DEIT, Swin Transformer, COAT-net, QuadNet, Uniformer. These are all convolutional networks powered by the attention mechanism, retaining skip connections to stabilize depth. Philosophical impact: preserving identity across innovative modules remains the backbone, even when pushing beyond pure convolution. So even we have pushed beyond convolutions, we needed the idea of preserving identity. So preserving identity is not limited to CNNs, but also is adopted by many architectures such as transformers and multi-head attention mechanism. And here we have a summary table that says we have the first pillar, retain identity at depth. So we have to retain identity at depth. Skip connections around every block, whether it was multi-head self-attention or it was feed-forward network. Enable global context. Self-attention attends across entire input. So rather than just learning local patterns, it learns global context. Combine identity plus attention. Residual multi-head self-attention plus feed-forward network keep signal and depth stable, keep signal and depth allowable, excel empirically. VIT outperforms CNNs on large-scale image tasks. So when VIT becomes better than CNNs, when you have large datasets, when you are dealing with lots of images, then in that case, Vision Transformers outperforms CNNs on large-scale image tasks. Preserve identity across hybrids. Models like DEIT and SWIN retain residual design. Here, as we said, we have some models like DEIT, SWIN Transformer, QuadNet, Uniformer. These models all use convolutions besides with attention, retaining skip connections to stabilize depth and also to stabilize signals, model performance and philosophical insights. So here we are comparing different model performances via this table. If you here take a look, we have AlexNet, we have VGG 19, we have GoogLeNet, ResNet, DenseNet, and until we have VIT. Let's compare between the accuracy and the number of parameters. AlexNet achieved 56.55 top 1 accuracy percent, while the number of parameters in millions 61.1. VGG 19 achieved 74.22 top 1 accuracy, while the number of parameters or the amount of parameters is 143.7 million parameters. GoogleNet achieved 69.78 with the amount of parameters 6 million.6. So you can see here that the accuracy of the VGG 19 is 74, but GoogleNet is 69, around 70. So this is about 70% accuracy. It's kind of close to VGG 19, but with less amount of parameters. So Inception uses a more efficient parameters. It uses more efficient ways to reduce the amount of parameters, and thanks to bottlenecks, which reduces the amount of parameters using a one-by-one convolutions as a bottleneck to reduce or to decrease the amount of parameters. Multi-perspective vision. So GoogleNet utilized multi-perspective vision, capturing scale through parallel filters. And also we have ResNet 50. It achieved accuracy as 76.13, and the number of parameters is 25 million parameters. So you can see we have now an increasing accuracy, and the number of parameters increased 25.6 million parameters in ResNet 50. ResNet, the main idea behind it, preserving identity, residuals, safeguard learning's original essence. DenseNet 121 achieved 74.4. So here we have, you can see the accuracy is close to ResNet 74.4, but the amount of parameters is 8 million, just 8 million. So DenseNet is using more efficient ways to reduce the amount of parameters. The main idea behind DenseNet is collective memory reinforcing knowledge by feature reuse. So the main idea of DenseNet is the feature reusing pattern. We connected every single layer to every other single layer via densely connected convolutional networks. So DenseNet has just 8 million parameters, and it achieved nearly 74% accuracy, which is close to ResNet here, but with reduced amount of parameters. Then we go to MobileNet. MobileNet, as we said, this type of architecture, this family of convolutional networks is best suited for embedded devices, best suited for mobile phones, and it achieved 71.88% accuracy, but with just 3.5 million parameters. So lightweight depth, enabling efficiency for mobile and edge competition. So this architecture is really efficient, so efficient, really using small amount of parameters, as you can see, but achieving 71.88% accuracy. So if you have some devices, if you have resource constrained devices, if you have resource constrained or resource limited devices, you may want to use MobileNet version 2, because MobileNet is using the parameters wisely. Reconstruct, or to go wisely, we don't need to go deeper and deeper, but instead we need to leverage the efficient use of parameters via separable convolutions, depth-wise separable convolutions, used in MobileNet version 2, inspired from Xception. Then we have EfficientNet B0. Efficient B0, they rethought how they scale the models. Instead of rescaling the model from just one axis, they rescaled or scaled the architecture using 3 dimensions: depth, width, and resolution. It achieved 77.69. So if you see here, they are the best across all of these. So across all of the architectures here we have the best is EfficientNet. EfficientNet P0 achieved 77 with only 5.3 million parameters. So compared to, for example, ResNet, and also compared to in GoogLeNet 6.6, and also compared to DenseNet. So the best one, or the best architecture here, the best performing architecture is EfficientNet. It achieved high accuracy with just 5.3 million parameters. Why? Because they rethink the scaling way of the architecture. They rescaled the architecture using the 3 dimensions. And then we have the last architecture that we discussed, which is Vision Transformer. It achieved 81% accuracy, so the best architecture with the number of parameters as 86.6 million parameters. Depth through attention, letting vision emerge via global contextual focus. So letting vision emerge via global contextual focus. And EfficientNet, the idea, thoughtful scaling, wise scaling, balancing depth, width, and resolution harmoniously. And if you take a look here, we have ConvNext Tiny. ConvNext is an architecture that achieved 82% accuracy, and the number of parameters is 28 million parameters. CNNs reimagined, blending convolution with transformer-like inductive priors. Philosophical insight: transformers forgo, in other words, forget. Transformers forgo convolutions in favor of attention-driven global learning, but they still live by the ResNet mantra: preserve identity at depth. The residual structure ensures signal integrity as models become deep and context aware. VITs thus symbolize a philosophical evolution, maximum expressiveness through global attention, grounded in the stability of identity flows. So the basic idea here is that the residual structure ensures signal integrity as models become deeper and deeper and deeper, and context aware via the attention mechanism. VITs thus symbolize a philosophical evolution, maximum expressiveness, maximum expressivity through global attention, grounded in the stability of identity flows. And here we have this paper, featured paper, Vision Transformer 2020. It was introduced in 2020. An image is worth 16 by 16 words. So an image is worth 16 by 16 words. Transformers for image recognition at scale, by Alexei Desvodsky and et al. So we have here the image of the author, Alexei, transformer encoders plus patch embeddings plus identity residuals. We show that a pure transformer can generalize surprisingly well to image classification, provided it is trained on large scale datasets. And you can have a read to this paper. So you can read through this paper by clicking view inline. An image is worth 16 by 16 words. Transformers for image recognition at scales. So they used transformers for image recognition at scale. And then you can read the abstract. So here, while the transformer architecture has become the de facto standard for natural language processing tasks, its applications to computer vision remain limited. In vision, attention is either applied in conjunction with convolutional networks or used to replace certain components of convolutional networks while keeping their overall structure in place. We show that this reliance on CNNs is not necessary, and a pure transformer applied directly to sequence of image patches can perform very well on image classification tasks when pre-trained on large amounts of data and transferred to multiple medium-sized or mid-sized or small image recognition benchmarks, ImageNet, Cypher 100, VTab. Vision Transformers attains excellent results compared to state-of-the-art convolutional networks while requiring substantially fewer computational resources to train. So you can read through that architecture or through that paper, and we have here the same image. Okay, so we have here the image, we have segmented it into patches or into segments, and then we pass it to a linear projection of flattened patches. We flatten them, and we provide it with a positional embedding. We provide the transformer with positional meaning because it doesn't learn the meaning or doesn't learn the contextual order. And then we have to apply the transformer encoder and pass the outputs to a multi, which is this here. We have embedded patches, pass it to a normalization layer, then multi-head attention layer. Then we add some residual connection to preserve identity. Then we pass it to another normalization layer and preserve identity with passing it to a multi-layer perceptron layer. And this multi-layer perceptron head classifies into the classes bird, ball, car, etc. And you can go down and read through that architecture in your own time. You can see that they have these images input, and the attention makes it like this. You can see the attention mechanism learns the features, learns the patterns, and focus on the most important objects. It focuses on the dog's face, it focuses on the airplane itself, and it gets rid of the noise. It doesn't learn the noise, and here also it learns the most important features. And we can go deep down. You can see here RGB embeddings filters. They have visualized the representations that gets learned by the attention mechanism. So now we finished discussing about VITs and vision transformers, and also we have finished discussing this comprehensive CNN Architect Mind Atlas. We have gone through a long journey from LeNet, which was the first CNN architecture proposed in 1990s, and go all the way up to AlexNet, VGG, Inception, highway networks, and also we learned about the pathways of remembrance, ResNet, wide ResNet, DenseNet, Xception, MobileNet, EfficientNet, and also lastly transformers. And you can see a pattern here. Here we have a story behind each architecture. Each architecture taught us a lesson. LeNet taught us about the operation convolution. So it introduced the convolution operation. It introduced the convolution layer as a building block in deep learning. So if you want to teach models how to see, if you want to teach models how to look, you have to embed convolution layers. Then AlexNet taught us about how to go deeper and deeper by using GPUs. So if you want to train deeper and deeper models, you have to use or utilize GPUs, graphical processing units, and also you have to use ReLU as a function to faster convergence or for faster convergence, because LeNet utilized sigmoid and tanh and they were slow to train, so we have to use ReLU activation functions, and also you have to use dropout to prevent the risk of overfitting. So we have three important lessons from AlexNet: ReLU, or first GPUs, ReLUs, and dropouts. And VGG taught us about the pattern or uniformity. And as we said, we have three pillars important in VGG, which were the first, simplicity. So they used simple kernel sizes. Also uniformity across the whole architecture. So they used 3x3 kernel size across the whole architecture. And also they used the concept of simplicity to make the architecture uniformed or consistent across the whole architecture. And VGG, by the way, learned whole components. When at the last layers, it captured real whole components like the bicycle, for example, bicycle components. It learned the eyes, nose. It learned whole objects. Then we have Inception or GoogLeNet. taught us a lesson of parallelism, so how to see different things from different perspectives, how to look from different lens, how to look from different glasses. Here we have seeing multiple scales with one glance. So with one glance at parallel or in a parallel way, we saw the image from multiple different scales. And also they introduced the bottleneck operation, which led us to reduced amount of parameters. So this is a reasonable way. If you want to see from different perspectives, then you will end up with a huge amount of parameters. And to prevent this amount from getting huge and huge, or from getting larger and larger, you have to do a bottleneck operation to reduce the amount or to decrease the amount of parameters. So the philosophy, seeing multiple scales, seeing from the 1x1 convolutions, 3x3 convolutions, 5x5 convolutions. So the 1x1 convolutions learned the fine-grained detailed local features. It learned the detailed features. 3x3 layers learned mid-level features like the edges, textures, and 5x5 learned global features, global or complete components or objects. And then we have highway networks, which introduced the idea or inspired from the LSTM, long short-term memory. They inspired the idea of memory or for preserving identity via skip connections or bypassing data through the architecture. And they asked, do we need to go all the way to the end of the architecture, or do we need to learn how much each input needs to go, how much each input needs to go deep? Maybe we don't need all the layers. Maybe we need to carry the input and skip over the layers. Here we have this architecture. As you can see, we have carry gates, transform gates, and this was learnable. The gates was learnable. The architecture learned when to pass data and when to perform transform, whether you want to apply transformation or to pass data across the architecture. And then we discussed the idea of, we have now a landmarking idea in deep learning, which is pathways of remembrance. The architecture goes deeper and deeper, and the more you go deeper and deeper, the architecture will forget what it learned. So in order to make the architecture, its mind refreshed, and to have the mind of the architecture remember what it is learning, in fact, then we have to recall the architecture what it is learning by preserving the identity, by passing the data through the layers, and also and every time you are making the layers remember what it was learning. Then we moved on to ResNet. ResNets applied these ideas via skip connections. So as you can see, skip connections, and also they emphasized the idea of residual connections. And then we asked, maybe we don't need to go deeper, maybe we need to go wider via wide ResNet. We learned that wide ResNet architecture asked the question, depth is not alone, widen, reorder, parallelize. So we have three important aspects. We have the aspect of parallelism, reorder, width, because maybe when you go deeper and deeper, the architecture will not learn useful features. Maybe you need to go wider and wider, and this is the first thing. Secondly, they reordered the operations. So rather than starting with a weight layer, which is convolution layer, and then passing to a batch normalization layer, then to RLU, we started with a batch normalization layer, then passed the outputs to a RLU layer, then passed the outputs to a convolution layer, which is the weight layer. So they reordered the operations, and also they emphasized the parallelism as the Inception, learning multiple convolutions at one glance or in one hit. Then we moved on to DenseNet. DenseNet asked the question, maybe we didn't need to pass the data across the layers, and every layer just learns the identity and what the previous layer has learned. So not just learning what the previous layer has learned plus the residuals, which is the real image, but also maybe every feature matters. Every feature may contribute by densely connecting them. As you can see, we have densely connected the layers. So every convolution layer will see the inputs we'll see the outputs of all other layers. As you can see, we are passing, or we are connecting all the layers by each others. Every feature matters. Every feature will contribute to the learning. And then we have Xception. Xception emphasized on the idea of separable convolutions. So maybe we need to separate the idea. Maybe the convolution isn't able to learn features because we are applying just one kernel across the whole channels. We are applying just one kernel to learn the spatial dimensions and to learn channel dimensions. We applied one kernel per channel, applied one filter per each channel. So this was called depth-wise separable CNNs, and it was introduced by Xception. Philosophy decouple spatial and channel representations. By decoupling them, or by separating spatial learning and channel learning, it introduced a new concept of depth-wise separable convolutions. Then we moved on to MobileNet. MobileNet asked the question, what do we need when we have almost nothing? When you have resource constrained devices, what do you need to apply these? What do you do when you want to apply a net on the devices that has low storage or low computing power? Then it is not in excess where intelligence matures, but in constraint where it is redefined or refined. And as we said, how the Architecture Alliance also they inspired the idea of depth-wise separable convolutions, deconstruct to reconstruct, to build wisely, deconstruct first. And they also emphasized on the idea of that, what if you wanted to apply deep networks on devices that doesn't have that much computing power? And then we have EfficientNet. EfficientNet focused on the idea of scaling, scale in balance. So EfficientNet introduced compound scaling, not just scaling by one axis, but jointly tuning depth, width, and resolution based on principled search, and they assigned different coefficients. For example, depth alpha, width beta, resolution gamma, and they controlled these three coefficients via one constant ratio, which is phi coefficient. And then we moved on to transformers, and beyond convolution, preserve identity. So we have the first architecture that introduced the attention mechanism into the world of vision. And I think now we finished discussing all of the architectures. That was a brief overview across all the architectures. I think now we have finished discussing all of these architectures. This was a complete, comprehensive CNN architect mind, discussing the architect mind or the philosophy behind each architecture. So I think now we've finished discussing the whole ideas or the core ideas behind each architecture. And thanks for watching. See you soon.